Alright, game on. How are we doing, everyone? Just to make sure, can everyone hear me? Always the first check, just to make sure that my mic and setup are all working. I mean, they probably are, but it's always good to know. We've had some lively discussion in chat already, because I hopped on a few minutes early to see if anyone was online, and people have been talking about things like challenge questions, people jumping ahead and learning about arrays and things like that, and details about the compiler. So it's always good. Like every little discussion that we have about this is going to add a little information to what everyone knows. So I think it's just really nice to be able to have those discussions. Oh, hello. Somebody's down here. Maybe she wants to come up and say hello. Come and say hello, chicken. Yeah, there we go. Alright, a little bit of pre-lecture chicken. She just woke up. She's been like asleep on my bed for like the whole day, I guess. And I don't know, she just chose this moment to come up and say hello. Yeah, people saying the Spiral one was hard. And Jeffrey saying, done some programming before, absolutely did not prepare you for this. I hope that you see that as a good thing, Jeffrey, because one of the things the challenge questions do is they get you to think differently about the way that you're using code and think about difficult problems. Because as I've been trying to point out is that there are several aspects of programming. One of them is, yes, just grasp the language. I'm just gonna going. Yeah, there you go. Because she's sitting right here, right now. So I figured you might be more interested in her than me. So this side of things is to get you to think about the fact that what programmers do a lot of the time is we solve difficult problems, and that is one of the important things that we do. Is there's a lot of stuff about trying to find our way around things, and we're using the computers to find our way around things, rather than just thinking about things as the problem's already solved and we just need to translate it into computer code. What's sometimes very important is us trying to find out what the solutions to the problems even are to begin with. Jen's asking if we get to see chicken fed today. We probably will. Oh, look at that little squinty face. Hints on order 3. I'll let you ask your tutors about that. I don't want to give like super hints out to everyone. Okay. Liang Chao saying, is there something for C like stepping through breakpoints? There is a program called GDB, but GDB is quite fiddly to use, and so it's kind of hard. If you use something like Visual Studio Code, there are other things like that. Ah, Shrey's here. How's it going? Okay, so yes, and everyone's saying Spiral and Decimal Spiral are very hard. That's true. Spiral and Decimal Spiral are quite hard. I mean, yes, they're designed that way, and if you're worried about them, please don't worry too much. The thing that we want you to understand is the idea that if you loop through data, so whether it's looping through a single array or we do this double array thing, and sorry, I said array, we haven't taught you about that. Whether it's a single loop or a double loop, and you're going through all of these possible spaces, you want to be able to check each space for different conditions and then do different things depending on what's in the space. So it's kind of like you're just going through code, and when you have an if statement, you decide whether or not to do something. So if you're going through your code and it's not necessarily just once through the code, but it's in a loop, and every time you go through the loop, you're checking a different kind of value, then each of those could have a different result based on an if statement. And that's the kind of structure that we're trying to teach you about. Because it's very important, and it's used a lot. I'm just going to... Look, she's looking right at the camera. I don't know if you can hear that, but she's purring now as well. Okay. Terry. Will the last question be as hard as Decimal Spiral? Probably. It's a bad thing to talk about the final exam now. Um, I'm going to tell you, I'm just going to tell you my overarching theory about the final exam, and then we're going to go into the lecture, because this is not the time to talk about the final exam. I have a whole lecture about the final exam, which will be done at a time where you'll actually remember it when you get to the final exam. But the theory for the final exam is that um, the idea that everyone should complete it is a silly idea for an exam. It's a silly idea for any exam. The whole point of an exam is to assess how well everyone's doing. So the only way to assess how well everyone's doing is to make the exam so hard that no one can complete it. If I make the exam so hard that no one can complete it, then I can see exactly where everyone's up to. So it is not it's not feasible or even reasonable to think that you should complete an exam. Completing an exam is not very useful to us as a university. You won't get very good feedback out of that. So if I gave 100% to 90% of the students in the class, so I just gave everyone full marks, then I have no idea how good everyone is. And that's the whole point of the exam. It's an examination that's meant to find out how good everyone is at what I've taught you over the last 10 weeks. So the only way to find this out is to what we call in engineering terms a destructive test. Sorry. I just gotta laugh because I know that as I'm saying that, everyone's like, "What? My brain? No, please don't hurt me." So when they do this in structural engineering, what they do is they build, say, some chain or some rope, some stuff that's designed to, keep people alive when they're like suspended off things and stuff. And so what they will do is they will test this until it breaks. So they'll test it all the way until it breaks. And if they know at what point this chain breaks, then they can say this is how strong the chain is. Exams are the same thing, only we're doing it to your brain. So I always got to laugh when I talk about stuff like this, because it is a bit like that. Obviously, I'm not trying to hurt anyone by this, but what I'm trying to do is find out where you have to stop. So every student reaches the point where they say, I have exhausted my knowledge of this course. There is nothing more that I know that I've learned. And if I can find out where that point is for everyone, that's how I know what marks to give you at the end. So that's why an exam has a question potentially as hard as something like the decimal spiral. Having said that, I am still happy to say that anyone who this is not only, by the way, anyone who gets 50% of the marks in this course is more than ready to move on to the next course, is happily able to go on to the next things. And you won't know everything that I've taught you, but you don't need it all right now, Like, some stuff I teach you is just there so that you can see it once. Because this is a teaching thing. I can't remember if I've spoken about this earlier. I can show you something once, and then someone else in 6 months' time can show it to you again. And even then you might not get it. But then a year later someone else asks you about it, and then you'll talk about it and you go, oh, hang on, I know a lot about this. Even though every time someone's taught me this, I felt like I didn't get it. That's not really a problem. I don't really have a problem if you don't feel like you get something, because eventually you're going to be like, oh, I kind of, like, in all those times I thought I was failing, I was actually slowly absorbing information. And we're much better at absorbing information slowly than we are quickly. So, like, I don't even mind if people don't get some of the harder stuff in the course. So, for example, the idea of, like, how to do spiral. If I ask someone in second or third year comp-sci to do that, they'll be able to do it. And I trust that the majority of you will be able to do that once you get a bit more experience. So even if it's a bit weird now and things aren't working out, that's only because you're on a path and you're just earlier in that path. Like, it's not that hard to walk this path, but it does take time. And so eventually you'll get there. So it's not really that big a deal if you don't know stuff now. But it is useful to look at it. It's useful to look at it and see it and just go, I don't know how to solve that problem, but I can solve simpler versions of that problem. So if you can solve the X, or you can solve the harder one like the hollow triangle and stuff like that, some of that stuff is well on its way to teaching you how to do the other things. But one of the most important things about learning is having the patience to let that lesson simmer and let that lesson kind of percolate through your brain before you necessarily try to break yourself on the more difficult problem. So I should point out that I have people tutoring for me. So people who I say are like the smartest people I have, the people who can transfer the information in the best way to you, who didn't even bother attempting decimal spiral because it's too hard, and that's fine. You know, it's not really a problem. But it maybe got them thinking about what possible solutions they could have for it before they went off to do some other work instead, right? Because no one has an infinite amount of time to spend breaking themselves on challenge questions. Some people will enjoy it, but it's not necessarily recommended, right? Okay, so I just go back through the chat and it's like Mark's trying to break us. uh, uh, okay, so yeah, all right. Oh, should point out to everyone. Oh, hi Tom, how's it going? The first weekly test was released early this morning. I was thinking about releasing it later and making it due later, but I thought I'd just release it early anyway. It doesn't matter. You have another day to work on it. So we're going to try to release them on Thursdays, but I've shifted the due date. So I know the course outline says it's due Thursday, 5 p.m. I don't want it due in the middle of the lecture because I think that that's going to be like the first hour of the lecture with a whole bunch of people cramming to finish their weekly tests, and I don't really want that. So I've made it due later in the evening on Thursday instead. So I know students will never complain if I give everyone an extension on something, so I pushed it later rather than earlier. It's like make it due at 4 p.m. and everyone will be like, no! But made it due later on in the evening, so it's going to be due on Thursday next week at... When did I make it? Did I make it 8 p.m.? I think I made it 8 p.m. or 9 p.m., something like that, later on in the evening. Okay. Someone said they forgot about the weekly test. Don't worry about that. It only takes an hour to do, and you have 7 times 24 hours between now and then, so you've got plenty of time. It just depends when you want to set aside the time to do it. Up to you. Yes, yes, as Tom is reminding us, it's due next Thursday. It is not due tonight. I don't release the weekly test and have it due on the same day. That is... So, after me talking about how mean I am about the exams, but justifying it, I'm not mean enough to have something released and due on the same day. Until the exam, obviously. But that's a 24-hour exam. That's a special thing. But in terms of your assessments, where I'm saying you pick the time you want to work on it, like something like an assignment or the weekly test, I'll give you a few days at least. So you have a full week to work on the weekly test. Yeah, and it'll be due after the next lecture. And it's also based on earlier content that we worked on as well, because it's meant to be the final thing you do from like week 1, week 2 content. So it doesn't even have week 3 content in it. Right, Tom's clarifying that I made it due at 20, which is 8 p.m. Looks like my upstream is jumping around a bit, so hopefully it's not too bad. No, Terry, it's not a snake. It is a tail of a chicken. Okay. Pooja's just asking about what we test on, and it's usually the weekly test will be from the lab work from the week before, which is from the lecture work from the week before. So, for example, it's going to be week 1 lectures, week 2 labs tested in week 3. So week 2 lectures, week 3 labs will be tested in week 4. We'll have that kind of thing until we get to the end of the term where we don't have like a week 11 to test the week 10 stuff. So we'll kind of shift some stuff a little bit forward there, but not too much. Oh, people are asking me to turn my volume up. It's a bit quiet, is it? And someone also is asking if we're supposed to do the tutorial questions before the tutorial. No, not necessarily. You can look at them. It's also good to look at them. Let me just go to my audio. Alright, I'm just boosting my my audio a little bit. Okay, see if that helps. I've just boosted it a little. you can look at tutorial questions, but they're actually going to be worked through in the tutorial. So it's not something that you have to do in advance. You're not expected to know everything in the tutorial before the tutorial happens. A lot of the stuff in the tutorial is us expanding what I've taught you in the lecture, so it's not necessarily something that that we expect you to be able to know after the lecture and then have the answers in the tutorial. It's more that in the tutorial, these are the things we're going to work through. There'll always be leftover questions in the tutorials as well, because I usually write more questions than we need. So that way you've got a bunch of revision bank questions on particular topics as you go back. Okay, let's get into the lecture itself. So, what were we learning last week? Last week we put a bit of time and effort into code style and code reviews. So we were thinking about, did I say last week? Last lecture. Tuesday. I'm gonna say yesterday again. I say yesterday because like when I finish lecturing, they freeze me, and they put me back into the vat to be put into storage until they need me again, and then they thaw me out like just an hour before the next lecture, and I lecture unit 01 gets put on display, right? Okay, so we're talking about writing code for humans, and it's about making sure that the code that we write is understandable to us in the future, is understandable to other people that we work with. And we showed an extreme example of if we don't do that, how hard it is to figure out what was going on. Someone did pick up on it, which was really cool. It's always funny to see, did they just do a really high speed go through the code and fix it all? Or did they actually see it when the code was in a bad state? It's actually really hard to see the error when the code's in a bad state. And then we had a look at functions. So we had our first look at what functions are. I introduced this just as sort of topic material, but not necessarily how to use them. So this week we're going to do a little bit more practical, not this week, this lecture, we're going to go a bit more practical and actually write some functions, which would be pretty handy, I think. Okay, so today I'm going to talk a little bit about the theory of a computer, because it is nice to understand what this thing is that we work on, because we sort of treat them as these tools that we have available, and we just like, yeah, we know we run like an operating system like Windows or OS X or something on it, and we know that we can, we can surf the internet, and we can play games and all this kind of stuff, but that's a very abstract way of thinking about it. When we start to think about it closer, we want to use this thing as a tool that we can actually do stuff with. It's really handy for us to be able to understand what the theoretical concepts are behind it. And it's not just theory. I'm going to look at some of the actual practicality of how our programs sit physically on our computer somewhere in those memory chips, and how we actually use it. Obviously, this is an overview. This is an introduction to programming, not the be-all and end-all of exactly how computers work, and you'll never need to learn anything else. Like, I'm not going to say that after today's lecture you can build your own computer or anything, but you'll understand the theory of it, I think, a bit better. And then we're going to go on to this thing called arrays. Arrays are a way of us collecting multiple variables together in a useful collection, and being able to work on them as a group of variables rather than as individual variables. And we will do an example that uses arrays as well as the functions that we learnt on Tuesday, because we're obviously not done with functions. Like, all I did was just briefly introduce them, so we're going to work on them a bit more. Alright, looks like Shrey and Tom is talking to people about things. Yeah, okay. I'm just going to let Shrey and Tom answer all your questions there. Okay, so what is a computer? When we think about the computer at its most fundamental level, this means we're going to take away a lot of stuff that a computer is that's over and above the raw basics of what it can do. A computer has a processor, and the processor is the thing that says, the code told me to do this, so I will punch some numbers and make that thing happen. And the computer has some memory, and the memory is the part of the computer that stores information. So the part of the computer that says, I need to remember that this is this kind of data, or even that like these are the files that are on this computer. Like I'm going to call that memory as well. It's like longer term memory. People tend to call it storage and stuff, like what's on your disk. But yeah, at the most fundamental level, there's only two things. There's the doer and the rememberer. Technical terms. We tend to call that the processor and the memory of the computer. So remember in week one, we were talking about Alan Turing. Alan Turing was someone who did a lot of computing work around the midway through the 20th century. So worked with the British in World War II, worked as what you would have called a theoretical mathematician at that time, until they started being able to put this stuff into machines and became one of the first people to sort of open up the world to this computing age, like to actually build a computer and use it for practical purposes. He came up with this idea for a Turing machine. And it's a completely theoretical idea. I mean, you can build them. It's a physical thing, but it has some theoretical concepts in it that are impossible to build. So there's a piece of tape. So it's like a piece of paper that's infinitely long. So back then, tape wasn't just tape that had a sticky side. Back then, like tape was like, you know, like what your receipt is printed on if you go buy stuff and get receipts. And a head, which was a little thing that could move back and forth along this tape, and it could read what was drawn or written on the tape, or it could write things, and so it could erase things and write over things. So this thing could go back and forth along this tape and change what the values were on it. There's also a state, so in that head, there's a thing that remembers what it's up to, and there's a set of instructions that says, depending on where I'm up to and what I read from the tape, this is what I'm going to do. And a lot of this, I think, should be kind of pinging things in your memory, because it's kind of like, well, the program has a state. When we run a C program, the state that we can think of it is what line of code we're up to. And what line of code we're up to says what we're going to do next. And then what we're going to do next might be to access a variable, which means we can move back and forth along our tape until we find our variable. And we go, okay, we're going to use that variable to do something, right? And so we can see how the early programming we've done fits in with this idea of the Turing machine reasonably well. Here are some pictures of potential Turing machines. There's a really complicated one here, which is using magnetic tape, I think. And so you could actually build this if you wanted to, using old school technology like a VHS or a cassette machine. Like, you know, that used to be like what we do. I don't know if anyone has heard of like the Commodore 64 or that era of computers. We usually used to have programs that were on a cassette tape. So you could put it in your tape player and play it, and it would make these weird buzzing noises. But we would actually play that tape into the Commodore 64, and it would read the tape, and it would read the ones and zeros off the tape and load the program. It was horrendously unreliable, but you know, it's as good as you get at the time. So we can move back and forth, and we can change whether things are ones or zeros on this tape. One of the funniest ways to think about this, and this is like one of my it's still quiet, so my mic is still let me boost it a bit further. It's weird because my mic is not usually, hang on a second, maybe I need to check my sound settings. What am I looking for? Control panel. There we go. Pump up to full. Are we better now? Oh. We might be better now. I just spoke then, and my meters went all the way up to red. I may have to just turn the boost down that I had on OBS there, which is my streaming software. Because I just boosted it beyond maximum, which is probably not the right thing to do now that I'm on 100%. It was too much, wasn't it? Okay, now it's not maxing out anymore. I apologize about that. I'm not sure what I was doing because I hadn't actually done anything with the mic before to reduce it to 75%. So now both things are on 100%, so hopefully it won't clip either. So it's good. Okay, good. All right. Well, some people know about clipping and stuff. I always love it when other people are also audiophiles and things. Okay, so one of my favorite ways about this is this hilarious way of thinking about it is I am in a box. So I'm in a cardboard box like the size you have for a fridge, and there's some wheels on the bottom, and I can push this box back and forth along potentially an infinitely long driveway or something like that. And then on this driveway, I've got a piece of chalk, and I'm drawing ones and zeros on this driveway, and I can wheel it back and forth. And then inside the box, I've got a bit of paper that says, okay, if you see this, do this. If you see this, do this. And if you've done these things in this order, then do this. So that is the kind of thing that we're actually thinking about here. It is that simple. It's something that just says, do this under these situations. You can look at one bit worth of information at a time, and you can move along it back and forth. The interesting thing about this idea of Turing machines, is that there is nothing. And this is the weirdest thing about this, because when you think of something this simple, you don't think that it can do so much, but there is actually nothing that that our modern computers can do that this theoretical example can't also do. There is no mathematical calculation out of reach of this person walking along in a box that our computers can do that this person can't do. So none of the calculations, I mean, sure, it's going to be a lot slower, but the theory of it is that there's nothing that is capable of being calculated eventually by the person in a box that our computers can do. So they're no more complex than that. They've got a whole lot of stuff added on top of this. They've got a whole lot of stuff that is done just because they can do it much quicker than this, but the mathematical capability of the computer is nothing more than a person in a box. So it's interesting when it comes down to that, because when we think that, like, with this, it's been like 70 years or so since Turing, it's not exactly 70 years, since Turing came up with this concept, we have not necessarily advanced this concept to anything new yet. We're still moving back and forth in our memory on our computer and flicking numbers on and off. And that's all we're doing. Because when you think about it, if we change the value of a variable, that's us just finding which point on the tape the variable is and rewriting the ones and zeros in that section. There's exactly 32 ones and zeros in our integers, and we're just changing them until they're what we want them to be. So the little person dragging along their cardboard box has that capability. So it's really interesting, right? So the fundamental concept's quite simple. So when we think about this, the thinking bit is the processor. On a computer, we will call that the CPU. It's not the only thing on the computer that does processing. Those of you who are, like, especially people who are into gaming and stuff, will know that there's a GPU as well. It's a graphical processing unit that's made specifically for certain kinds of things to display them on our screens. The GPU actually has less capability than the CPU. There's a couple of things that it can't really calculate. So it's interesting that it's like the CPU, but it's more focused on a specific task. But either way, we've got a thinking bit, right? The CPU maintains a state. That's it saying, I remember where I am. In the simplest way we think about this, the CPU state is just what line number am I up to in this particular program. It's vastly more complicated than that, right? It's vastly more complicated than that. But it's okay to think about like that when you're thinking about it the first time you're delving into these concepts. So the CPU will be given a series of instructions. You could consider each line of code to be a series of instructions, but as you have seen, there are potentially multiple instructions in a line of code. So if I do something like total equals integers this plus integer that, well, not integer this, but like I have two variable names, so total equals x plus y. There's several instructions there. A couple of instructions are going to be like, go look in memory for x, give us a value. Go look in memory for y, give us a value. Another instruction that says, take those two numbers now, add them together. And then another instruction after that says, now take whatever value that was created out of that and write it into this other variable called total, right? So if I have a simple line of code, it actually has multiple instructions. But our CPU is okay because it's doing several billion instructions a second, so we don't really have to worry if this thing has to get broken apart into all these different pieces and do things. That's what our compiler actually does for us. It takes that one line of code that we write in a way that humans can mostly understand. I say mostly understand because, like, even those of us who spend a lot of time with code don't understand everything that we're writing. It's just the way it is. So the CPU is going to be able to work off those instructions that we give it, and can also go to memory and say, okay, I want to write something to memory, or I want to read something from memory. And this is what I'm talking about here. So the state is where we're up to, etc. So what is memory here? Are we okay with the audio now? There's some people still talking about it there, or maybe that was just delayed there. People talking about how expensive GPUs are. Luca Buonamano says, except quantum computing, and that is a good point. Quantum computing is the first step that we've made in computing which takes us outside of Turing machines. So it takes us to this weird world where those ones and zeros might be ones or they might be zeros, and they could be both at the same time. So that, I think, is the first computer that we've created that that goes beyond the Turing machine. But all the computers that we're using here and now, all the ones that you're learning how to program for the moment, are these standard computers, which we call Turing complete, which means they can do the same thing as the Turing machine. Okay, so the memory itself, and now we're going to go into slightly more details about this. I'm going to call everything where we can save information, so we can save ones and zeros on the computer, memory for now. It's kind of data storage kind of memory. You know, people tend to think of memory as one specific part of this, which is the RAM, they call random access memory. This is one of the numbers they use to sell people computers. It's like, this computer's got 64 gigs of RAM. It's like, some computers actually do have 64 gigs now, right? I think I'm running off 16 gigs of RAM here. There's nothing in COMP1511 that's going to need any more than, like, I don't know, 1 megabyte of RAM, because, like, we're teaching you how to code a computer at the basic level. We're not necessarily teaching you how to do, like, effective simulations of light bouncing off objects and stuff, which tends to take up a massive amount of memory. Or can you predict what the stock market will do tomorrow, which means you need, like, vast sums of memory of, like, what the stock market has done over the last 20 years to see how trends and flows work and stuff like that. So we're not worried about all that kind of stuff. We're trying to learn how to program in its most basic sense, so we don't need that much of this. However, the memory in our computer is separated along this spectrum. So the hard drive is slow in terms of, like, if we take the old school hard drives, they're actually a spinning disk of magnetic material. I don't know exactly which magnetic material it is, and a little thing that reads off it. So this thing spins, and it spins at 7,200, well, on average, they don't all spin the same speed, 7,200 times per minute, which is, how many is that? It's just over 1,000 times a second it'll spin. So every time it comes around, you can read some data off it, and then it comes around again. So if that's coming around 1,000 times a second, that's pretty quick. We're getting a lot of information off that. But excuse me, maybe I should put a jumper on in a second. I said that our CPU could do billions of things per second. So if the hard drive is spinning around 1,000 times a second, our CPU can do 1 billion operations a second. I'm just really ballparking these numbers here, right? These aren't exact numbers. You want to look up exact numbers, you can look up how many gigahertz your processor is and that kind of thing. But the difference in speed here is massive. Because if I can do 1 billion things and there's only only once every 1,000, a thousandth of a second that I can pick up stuff from my hard drive, I can waste like 1 million goes of my CPU just waiting for the hard drive to give me information. And I don't necessarily want to waste all those millions of things. So I get faster storage. And that's where RAM comes in. a RAM is actually chips, and you can like slot them into your computer. And on your RAM, you have memory that works much quicker. So RAM also works in the range of gigahertz. So it's working not quite. Actually, I don't think there's gigahertz RAM, right? I think it's megahertz RAM still. But it's much faster than the hard drive, but not as fast as the CPU. Anything that can give you back and forth sort of information that quickly becomes more expensive. So that's why there is not as much RAM as there is hard drive space on a computer. And again, even at the next level of that is the registers and cache that you would have heard of, maybe. Some people sell CPUs based on how much cache is on them. That is stuff that's physically on the CPU. So the CPU is a block of silicon that has these thinking bits in it. It usually has multiple of them. But also there's some space there on that. You can look up diagrams of them as well. They're in these really cool rainbow colors from like how they're built. There's some information there, and it's a very, very small amount of information. Nowhere near as large as what's in the RAM and the hard drive, but it goes nearly as fast as the CPU. So what we end up with is this hierarchy of storage. And the interesting thing is, when you turn off your CPU, it's going to lose everything that it had remembered. When you turn off your RAM, it's also going to lose everything that you remembered. But when you turn off your hard drive, it stores it, so that when you turn your computer back on later, everything that was in your hard drive is still there, but a lot of the stuff that was in your RAM and your CPU is going to disappear. So we have this idea that there's faster but smaller and more volatile stuff that we're going to use for processing things, and then there's larger, slower things that are more permanent, that can last, like a hard drive can last a few years before the data starts degrading on it. Whereas RAM, once you turn off power, you've got a few milliseconds of those switches staying in place before they all flick back to nothing. So this is just like, okay, I just want to point out, all right, I only spent 5 minutes on this, but oh yeah, people are talking a little bit about like the speed of RAM and that kind of thing. So if you want to get into this, there are more courses that will go into like this in great detail. We could spend a 10-week course just talking about structures of memory, and how we move things in between the hard drive, the RAM, and the registers and stuff, and why we do things in certain ways. What does it mean to do this in a 64-bit system, and all this kind of stuff, right? It's a whole world of this if you're keen. But for the moment, I'm just going to do this 5 minutes on it and move on, so that we have a vague understanding of what this is. Again, introduction to programming doesn't necessarily mean I'm going to teach you how to build a computer from scratch, but I wanted to at least show you this stuff, because I feel like one of the most important things when learning how to program the computer is to at least have the base understanding of how it works. Okay, so let's look closer at what we do ourselves. When we're programming in C, how do we use the memory? So we've got that hard drive. So the hard drive is the long-term storage, and this is where our source code files are, so everything with .c on the end. And I think everyone's pretty used to handling what's on a hard drive, because I think if you've got the computer literacy to be able to use a computer, you have at least at some point saved a file, maybe you've moved a file around, that kind of thing. So if I just pop open my Explorer here, I should totally not do this. There's going to be like assignments in here and stuff like that. No, I'm just going to stop doing that now, just in case. I was just like, where do I go to show people something that isn't personal to me, that I don't want them to see, or course material that they probably shouldn't look at yet? And so it's like, I'm just going to close that. Anyway, you got your File Explorer, and you can move files around and things like that. Our code files are stored on the hard drive. When we compile our code, that's also stored on the hard drive. Oh, I just thought of a much better example. All right, let's open VLab instead, and I can look at the folders that I've actually made for you to see, rather than opening random stuff on my personal computer. Okay. So I've got my directories here. Let's go to lecture 5, our most recent one, and look at this. These are files on the hard drive. So these have been saved to semi-permanent memory. So some of these are the code files that we've been creating. some of these are the files that are created by the DCC program. So when we run DCC, it is our compiler. It will translate the stuff that we've written in this semi-human readable format into this definitely not human readable format, but very, very easily computer read format. Not all programming languages even do this. Some programming languages just give this level of code to the CPU, and there's bits in between us and the CPU that sort of translate it into this code as it's going. But these are the raw instructions that can go to our CPU, and our CPU can execute them. That's why it's called an executable file. So all of this stuff is sitting on our hard drive. Here we go, back to here. Yeah. When we go to run our program, all of the file, like that green file there, like that dice check program, will get copied into memory. So it'll go into our RAM, which is the random access memory, those faster chips, and then our CPU will look at that and go through the instructions and say, okay, each instruction, I'm going to grab that from RAM, I'm going to copy that onto the CPU itself. So I'm going to copy that into the cache on the CPU or into the registers on the CPU. I'm going to use all the correct keywords, but you don't have to remember any of this. It'll be useful to remember it if you do, I don't know, if you go ahead and learn about things at a lower level on the computer, like operating systems is a course in CSE, or digital system structures. I don't even know if we even still do that course, where we look at like the lower level, nearly physical components of a computer. So we'll copy those instructions, and then our CPU will read those instructions and go, okay, I'm going to do this, which means I'm going to do some kind of calculation. Whether that's find something in memory and change it, whether that's change something mathematically, things like that. The CPU will then know, based on those instructions, whether it's going to go to different parts of its memory and read or write numbers and things like that. So nearly everything that our programs are doing is taking something from memory, and based on what that thing is, deciding what to do somewhere else in memory. And that's just like having the little bit of paper taped on the inside of the box that I'm walking around in, telling me whether to go forwards or backwards and how far to go, and then what to change, what to chalk on the ground. So you can see how this all ties in together to that same simple theoretical idea. This is what a program will look like in memory. So when we start running our program, our operating system, be it Linux, Windows, OS X, whatever, no matter which one it is, it's always going to say, okay, program, here is a chunk of memory that you can use. So we can provide this for you and say, nothing else in the computer is going to come in here and start rewriting your memory. This is yours to use. You can do what you want with it. If our memory is like a one-dimensional piece of tape, it could look a bit like this. This is actually what C does, but it's not. It's different for different languages. But a program might end up like this. So we have our instructions here. This is the translation of everything that we've done with our code. And then we'll have some space for our variables. So all the variables we declared in our code, each one will have a bit of reserved space that it can use. And then we will have this empty space. It's called the heap, and a heap is just like a reasonably disordered pile, which means that here's all the open memory that we could use for things, and the stack here is the current state. So the current state here will be like, where are we in the program right now? And sometimes it'll be, here are some variables that have been created by the program partway through, and then they'll be removed later. So this kind of stuff is there. We're going to go into more detail about what this actual stack is later. The stack is a keyword where I'm actually going to teach you about the stack. I'm not going to teach you about the heap, but the heap is something that you may learn about in the future. But we are actually going to be using memory. You don't need to know exactly how this works, but it's nice to at least have seen this once. Okay, so in our program, we will have like this big chunk of memory, and then different parts of it will be used for different purposes. I say again, this will come up again later, and I don't really have the time or space to cover this in a necessarily proper way here, because I think we want to learn about how we can get computers to do things, not necessarily do an entire course about what computers are built out of. So I mean, like, what did I say for the hard drive? Some magnetic material, because I think different hard drives are made of different things, but I don't even know. You know, like, every computer scientist may be studying computer science in different ways. Like, for me, I studied highly theoretical things where, like, when you think of decimal spiral, I know, ooh, chills. When you think of decimal spiral, I was the kind of computer scientist that would work on a whiteboard until we'd get to a point where the decimal spiral was theoretically solved and never write the code. So that was like one of the things that I did when I was working in more AI kind of things, artificial intelligence stuff, is that there was actually very little need for the code. The code was there only to prove that what we were thinking was correct. And so that's one end of computer science. Another end of computer science is someone who is looking at where to place chips on a motherboard so that the speed of light incurs the least amount of delay between components talking to each other. And there's no way to say either one of those tasks isn't vital to computer science and isn't super important, but they're so different. So the field is vast, it's massive, and what I've given you here is a really brief overview of the theory of what our computation is, and a little bit about how physically our computer handles that computation. So what I'm giving you is, like, if I give someone a picture of the Earth, like just a picture of the globe, and say this is the entirety of what humanity lives on, apart from the International Space Station. There's a tiny little spot floating around it where humanity also lives. Then you'll get a picture of it that seems to make sense to a certain degree. But you have so little context for what happens once you zoom in and you get closer on any of these other parts. We can zoom in on one continent, it's completely different from other continents. So what I'm giving you now is just this picture of what a computer is, and then you'll have the opportunity to zoom in later on other things. But I wanted to give you this because I wanted you to start thinking about the fact that we have memory, we're going to use that, and the difference between the memory and the processor. I've sort of been sneaking this in as we've been going along the whole time, right? I've been talking about blocks of memory and things. But I thought that we should do this because we're about to talk about more thinking about manipulating memory than we've done before. So we're going to be using blocks of memory now and things. So I wanted to get into this before we go too much further. Yeah, and looking at the questions there, people are getting some information here. So people are talking about, yes, the CPU is the thinking bit, and the RAM is just temporary information storage. That is entirely correct. Cherry Blossom's asking that. People are saying, is the heap used up when we run the program? It is potentially used up as we create things. So the heap is like whatever's leftover space. The more program we run, the smaller the heap will get. We can actively use heap memory, but I'm not going to tell you about that yet because we're going to do it later. We are actively going to use the heap memory later as well. Curious Cat is asking me if I was a UNSW student. Yes, I was a UNSW student some time ago. And people talking about stuff like electrical engineering. Yeah, electrical engineering is where a lot of the computer hardware came from. So if we look back like 25 years ago, there was no computer science course at UNSW. I think 25 years maybe there wasn't one, but there was an electrical engineering course where they're starting to think about computing, and then they realized that this was a whole thing, and that's how the School of CSE ended up happening. Max G is saying, this is a really cool question, and this will come up in other courses. How do you code a compiler if the compiler compiles the code? Yeah, so at some point, humans have coded in the raw instructions that go to a computer. And it's super difficult. I have done a very small amount of it, and it's super annoying. Because even something as simple as add two numbers together is like an 8 to 10 line program. So you can imagine how much harder it is to do things, and you can't use proper variable names and stuff because everything's really specific. Look up the programming language called assembler, because assembler is like one step below C. When I say below, I mean more detail than C, and you'll learn a little bit about that. Um, the I think, yeah, and Shrey's saying there's a whole course on compilers, and Tom's saying COMP1511 if you want to learn about that, you want to get into that level of detail. The There's a game that's really cool. It's on Steam and it's on phones and stuff like that. It's called Human Resource Machine, and it's just really funny because you're a human, but you have to do the programming. Human Resource Machine is a game where it slowly elevates the challenges of what you need to program, but the more I played it and the closer I looked at it, I realized the entirety of Human Resource Machine is assembly. It is literally correct assembly code, apart from a bit of syntax. Right, you actually, by the end of it, you'll learn how to code assembly, so it's really, really funny. So if you want to do some coding in your spare time as well as coding for the course, a game like that's actually a lot of fun. I had a lot of fun with it. Anyway, let's talk about the next thing that I want to talk about, which is arrays. Arrays are where we... I'm just seeing what people are... Oh, someone said it's $15 on Steam. Anyway, okay, so I'm going to introduce you to a new type of variable. And I say variable in quotes because, yes, it could be considered a variable, but it could also be considered a group of variables. So arrays are when we collect variables together. So sometimes we want to have a bunch of variables together, and they're definitely a group. They're a group of variables together that have the same kind of context. But we don't want to have to declare multiple variables of the same type and then hopefully have some way of going through it. So I want to justify why we would use arrays. And I've actually talked about this example previously as I was talking about looping. So this hopefully should jog your memory a little bit. Let's say I want to collect everyone's marks. So I have marks for... Oh, I should have spelt this with a C. That would have been fun. Anyway, I've got marks for one student, another student, another student, another student. So I've got this big thing. And so for this course, there's 750 of you. So I've copy-pasted this line 750 times and then changed the name on each one, because every variable has to have its own name. Already I don't want to do that, right? Already I'm in a situation where I think, oh God, I don't want to have to write out all of these different variables. So already that's an issue. But there's another issue with that is, like, what if I want to check what grade everyone has? So I've got some if-else statements to be like, if it's over 50, it's a pass, or sorry, 50 or over, it's a pass, 65 or over, it's a credit, etc. I can't loop to access each of these integers separately, because each of these integers has its own name. And if I loop through code, I can only check one variable. There's no way for me to say, if I'm looping, I need to now check a different variable from the previous one. So I would have to go through and do all of these separately. So does this student pass? Does this student pass? Does this student pass? I'm at another thing where I'm doing 750 sections of code that are pretty much identical, except for this different variable name. Because I can't even do a loop that says do this student, then this student, then this student. It doesn't even really work yet. I say yet. There are other ways we can do this later, but only if we do it in a particular way. So if I have a problem like this, where I have multiple reasonably identical bits of data, and I want to be able to access them all, potentially looping through them all, I need another way of doing this, because this kind of individual variable, and oops, just press the wrong button. No, take me back to full screen. Okay. This is not going to work for me, right? There's prone to errors, and also just typing in this much code is just not what we want to do. So instead of this, we have an array. So an array is a way for us to have a collection of something like integers or doubles or any kind of data type. And if we have that collection, we can access it if it's a group, and we want to be able to do a loop so that we can loop through and we can see every single element that's part of this collection. So it's going to look a little bit like this. So a variable is a piece of memory on my computer. So if I say an integer, if I say I want to make an integer in my computer will assign for me 32 bits of RAM. So I have my 32 bits of RAM, and there's all the ones and zeros. I can change them to whatever I need them to be. An array is like multiples of that. So I can say I would like an array of integers here that holds 5 integers. And so what my computer will do then is, instead of giving me one block of 32 bits, it'll give me 5 blocks of 32 bits. What is that? 150? 160? I should not try to do maths like off the top of my head. Speaking of maths, I have had a chat with Daniel Mansfield, so there's something coming up soon. We just haven't figured out exactly what we're going to do. But yeah, we're going to do something silly. We may stream on both of our channels at the same time at some point. Okay, so the array is a larger chunk of memory, which is a multiple of the amount of memory needed to store something like this. So if I'm storing an integer, and I have 5 integers, then I have 5 times my 32 bits. And it's just one big block of memory. But what I can do is I can store multiple integers in there. Everyone's like, yeah, I love it. I don't think we can get Chicken and Charlotte in the same room. I nearly said Chicken and Charlotte, or Chicken and Charlotte in the same room, but we'll probably be able to get a chat going back and forth between them. Yeah, I'm not going to say anything more than that. I'm not going to spoil it because there's other stuff that we might be doing. Anyway, not to distract you further, so the way that we use arrays is that we'll get a cluster of memory where we have enough space for multiple of the same type of variable. Arrays are always going to be the same type of variable because we want to make it easy on ourselves and not have to try to store multiple different variable types in the array. But it's going to be, for example here, 5 integers in an array. One of the interesting things about this is that all of these integers will be under the umbrella of a single variable name. So the variable name will be the name of the entire array, and each individual element won't have its own variable name, but it will be accessed by a number. So each one will be like the first one, second one, third one, that kind of thing. The cool thing about this, right, is if each element is a number, then I can loop. Because if I loop through and I give each one and I access everything by its number name, then I can access the different integers without having to know all their individual names. So if I had separate integers, they would have to have individual names, and there's no real way to loop through a series of separate individual names. Whereas if they're identified by a number, I can loop through by just changing the number. Oh no, I think that's mean, Tiara. If we she's saying that Daniel and Mark battle out Human Resource Machine live streamed. I think it's a bit mean to have a programmer against a mathematician. Also, I've seen some of his videos and he talks about proving things and I'm just like, oh god. Don't. I did that so many years ago, I've forgotten how to do it. Okay, back to arrays. So here's some code for how an array works. An array works very, very similarly to a variable in that it has a type and it has a name. So one suggestion for the names of variables that I have is that an integer will be a noun. So those of you who forget English or have forcibly forgotten English because you decided you were doing a computing degree and you never use English again, a noun is a word for an object. So most of our variables are going to be objects. They're objects where we store values. When we have an array, we're going to use a multiple of that, so a plural, like array of marks. That's how I like to do names of variables. And so if I read this variable, it's pretty easy for me to see that because it's a plural, it's going to have multiple variables inside it. It's going to be a collection of variables. In terms of C syntax, we now have this square bracket. And the square brackets is the symbol of the array. So every time we're using an array, it's quite likely that we're going to be using these square brackets to do things. So the square brackets here, when we declare the array, tells us how many elements the array will have. So this is going to be exactly 320 bits worth of memory because each int is 32 bits and there's 10 of them, so there's 320 bits of memory there. So this is me claiming that much memory from my computer and saying, okay, this is how much memory we have. And then we can do some initialization. So there's a few different ways we can initialize. If we want to, using these curly brackets, we can put things in our array. The 0 is a special case, and this is what we're going to do as the simplest way to start our array of integers. If we do the curly brackets and 0, it just says every single bit in the entire array is 0, so the whole array has no information in it. Otherwise, if we want to, with those curly brackets, we can put in a list. So I could say, I want the 10 elements of the array to be single digits, 0 through to 9, and there's exactly the right number of them, 10 here. This will fit in there, and it will initialize it with those values. What are people saying? Tom's answering some questions. I'm going to let Tom answer those questions. Masony's asking, when we're writing arrays, do we always use square brackets? Yes. You can consider the square brackets to be like the word int, or like the word double, or like the word return, or if, or while. It's just like a keyword. Square brackets means arrays are happening here. So this means that we are creating multiples of this type of variable. So the square bracket definitely means there's an array happening. And later on when we use the arrays, the square bracket is actually used to access the array in particular ways, which I think is, oh, it's not this slide, it's the next slide. Yeah, anyway, I was going to magic that this is what I'm going to talk about now. But we are going to talk about how we access individual elements of the arrays as well. So, array elements. So there's the array itself. The array is multiple, is a collection of variables. I'm going to say variables because they're not variables in themselves. They're elements of a variable. But you could, if you want to, you could consider each single integer in this array. So I've filled out this array with some random information. Ooh, someone got an HD. But everyone passed. Isn't that? Oh, wait. Number 8. Anyway. So each element in this can be treated like a single variable. So each element can be treated as a single integer variable. And then here we have the indexes with which to access these variables. I'm gonna clue you in because this is the reason why I wanted to talk about theory of computers and memory and stuff like that, is the array itself. The array variable itself gives us a memory location. In the same way that an integer's variable name gives us a memory location. It says, here in memory somewhere, I have some 1s and 0s that have a value, and that value is an integer value that I can use in mathematical calculations and whatever. And you've even seen some of that in scanf, where scanf says, all right, I'm going to specifically give you the location of the variable rather than the value. So there's a lot of stuff going on in there. The array gives us this location, which is the very start of the first element of the array. And that's the reason why the first element's array is indexed at 0. So if it's indexed at 0, that means it is the first element. It's at the same memory location as the start of the array. An index of 1 says jump one element in and then look. Index of 2 means jump over 2 elements and then look there, which is why it starts at 0 and it doesn't start at 1, because the index is actually how far in memory do we go beyond the start of the array. So the first element is at the start of the array, so we don't go anywhere, so it's 0. And then the 10th element of the array jumps over the previous 9 to get there. It takes a little bit of mental gymnastics to be okay with this, but the more time you spend in computer science, the more time you will spend counting from 0 instead of counting from 1. So a lot of the examples that I've used leading up to this point, all the dice stuff that I've been doing has been starting at 1, just to kind of ease you into this. But now that we're using stuff like arrays, we're going to be most likely counting from 0 in our loops rather than 1. And so a few of you pointed this out when I was doing loops. It was like, why does he start the counter at 0 and then count up to 1 less than the number that he's counting to? And it's like, this is actually the reason why. Because of the way that the arrays are addressed. They're addressed based on how far into memory they go from the initial location. So that's why the first one is 0. So the other thing that happens, which is really interesting, is if we try to access an index outside of the array, so if I go for index 10 here, or index -5 or something, we're going to cause errors. So that's like me saying I'm trying to read outside of the information that this variable can hold. It's not exactly the same as something like when an integer overflows. That never leaves the memory, but because we're accessing a memory offset here, it's like how far in memory do we go from the initial location, we can potentially try to access something over here which is off the end, and that will cause errors. So we've just got to be a little bit careful of that. Little example here, element 2 of the array, so the element at index 2 here gives us 44, and the one at element 6 here gives us 62. So we're starting to get to the idea of, if we grab a certain element from the array, we're going to be able to read its value, and we'll be able to use it exactly like a normal integer, which means we can read and write from it. So we can read from it, do calculations, and we can write information into that space in the array. Jen's asking if we initialize the array, we're assigning indexes, or we're defining the elements. We're actually going to be writing the elements into the memory. The indexes are not allowed to change. So as you can tell, because the index is not assigned to this, the index is actually just a distance in memory away from where it started. So the indexes are kind of always going to be the same. Okay, some code so that we can see what we're doing here. For reading and writing individual elements, this is the declaration, same declaration that we had before. We're using the example of declaring it with all zeros. By the way, if you only put one number in, it can only be 0. No other numbers. You can't do it with other numbers. The zeroing is a very special case, but we're going to use it a lot, so I wanted to show it. So this makes everything 0. And note the square brackets. We use the square brackets to create the array. We can also use the square brackets to access an element of the array. These are not exactly the same square brackets. They are told apart by the fact that this variable type here says that we are making a variable, and if we just use the variable, it's not the same as making it. So we're going to use the square brackets, the universal symbol of the array, in two different ways. When we're making something, it tells us how big it is. When we're using it, it tells us which element we want to look at. So this is an assignment in the same way that we can assign a value to a variable. This is a variable because it's a single element of the array. So what I've said is take the first element of the array, make it equal to 85. Congratulations, you got an HD. So whoever's first in the roll gets an HD. Automatically, it happens. This is why I should have spelled this index of marks with a C. If I want to access another, oh, hello. If I want to access another variable in the array, I can do that by using an integer value, but I can also use it by using an integer variable. And this is where things get pretty useful. What are you doing there, chicken? She's knocking things over on my desk. That's how I can tell she's hungry. We'll probably feed her in the break. Yeah. So people are saying index is like a set that contains the elements. Well, index is not necessarily a set that contains the elements, but it's a way for us to find a part of it. And yes, and Tom's saying that, like, I may be showing this example with integer arrays, but we can have different types here. So we can have double arrays as well. So we've only looked at ints and doubles so far, but every variable type that we can make an array out of it. So anything that is stored in memory can be stored in a group in memory. Yeah. Okay. So we can, anytime we access an individual element of the array, we can treat it like it's an individual variable. So we can say one of them is equal to another. So we can say take the value out of 6 and place it in 2. But we can cause an error here by saying, all right, let's try to access something that's outside of the bounds. So this has 10 elements in it. If it has 10 elements in it, and I go to index 10 says, I'm going to skip over 10 elements and then look at memory. If I've skipped over 10 elements, then I've gone outside of the array. And we call that out of bounds, because the bounds of the array is like how much memory it has. And so if I've gone out of bounds and I try to write that memory, I could be writing into a different variable there. What's worse, I could be writing into the code that's supposed to run. And if I do that, then I could corrupt the code that's supposed to run next. So nearly every compiler at this point, not necessarily the compiler, but the running program at this point is going to say, whoa, well, you tried to write to something using that array that was outside of that array, I can't let that happen because you might break other parts of your program. I should I should point out this really funny thing here. You won't actually get this error during compilation. Oh, you might get this error during compilation, but I don't know. It depends on your compiler. Some of them are smart enough to look ahead for this kind of thing. Some of them will not, and you will only get this error when you try to run your program and you try to access memory you're not allowed to have. Super old school programming used to use this to hack computers. So it used to be that using this, you could access any bit of memory. So if you go far enough outside of this memory, you could find the memory that determined who did or didn't have access to this computer, and then you could rewrite passwords and stuff like that. It's a super old school hacking trick. It obviously doesn't work anymore. If it still worked, I probably wouldn't tell you about it. Hacking passwords is based on finding out whether people use their pets' names as their passwords or not. Strangely enough, chicken is not in any of my passwords. Okay. So, another thing is the reading and writing of arrays. We can't printf an array. So I can't printf an array and expect the whole array to appear. I also can't scanf a series of numbers into an array, but we can do it for individual elements. So anytime we want to access all of the elements of an array, we're going to want to loop through them and access them one at a time. So, for example here, if I want to scanf into a single element, I can do that. If I want to printf a single element, I can do that. Each of these things work very similarly to if they're individual variables, but I can't do this. So I can't scanf in 10 integers and put them all into the array like that. So I don't have that level of control over it. So if I want to do this scanf thing, I'll have to loop through and move my index through the array and write something into each one of them. Okay, so let's hit break time now. Tom's saying we still do. You still use array out of bounds to crack people's code? I didn't know that. I haven't done security recently. I thought people plugged a hole that was that simple to get through. Oh, people are asking about access index. Let me go back. So this is another variable. Oops. I can't highlight that because I'm not in edit mode. This is showing that in order to access an individual element of the array, all we need is an integer value. So it doesn't have to be a specific integer value like this 0 or this 2 or this 6. It can be the integer value of a variable. So we can use a variable to access a part of the array. So this doesn't actually have to be an explicit number. It can be an integer variable. People are like, oh, Mark just told us how to hack. I mean, if there's going to be a significant number of you who are going to be interested in how to secure systems in the future, and if you don't know how to break into them, you don't know how to secure them. Masony. Can you have a number between the square brackets as a variable which can be ++ed and looped in a while loop? Yes, you can. So we're going to do this. We're going to do this in the second half. You can put an I in here, and you can loop through from 0 to a certain number, which is why I showed you the loop that loops through an exact number of times. And that way, what you'll do as you loop through is you will access every single every single variable that's inside the array, like that. Okay, people are just talking about other stuff. Okay, I am going to go on break here. And I thought that this I could have put this break in last week, but I thought I'd let it simmer for a bit in this week. And it's like, here's this hilarious thing, because I think now we're getting into more complex code. People are starting to think about how do I write the best code, and it's really hard to do. And there's all these different ways to approach it, and XKCD is a hilarious comic. So I thought I'd leave this here. You know what? I'm gonna leave this up, and oh, I need to get my face out of it so that you can see it as well. Maybe I'll leave this up on break time, and Mark, move your face. Okay, Tom, got it. Anyway, yeah, I'm gonna leave this up here for a break, and I will go get Chicken some food. And we'll do the feeding chicken in the lecture thing again. Alright, so I'm just going to mute myself but leave this screen up so you can see it for a second. Alright, I'll be back. I believe it's feeding time. Okay, let me set this up somewhere where you can see Chicken. Yes, Chicken, there you go. Is that? This is hilarious. Okay. So I am putting together a big campaign to try to get Chicken to be the mascot of UNSW rather than Frankie the Fox. Because Chicken is much less likely to get taken away by the council once they find them. Alright. Yes, and I do appreciate that people are saying Chicken is better than Frankie. Chicken won't bite course admins either. Yes. Oh, someone said, who is Frankie? Frankie is the name for a fox, or a family of foxes, because we didn't realize there was more than one that have been living on campus. It's all just fraught with, like, there's all these arguments happening on UNSW discussion, the Facebook group about it and everything as well. I mean, foxes are not native animals, and so people are a little bit like, they're actually a threat to native species, so there's a problem with that. But I think for other people, Frankie is just this sort of breath of fresh air in a time of great turmoil. So it's sort of funny to have this little animal that is actually very polite to people right up until the point that it bites them. So it makes us all think that that it's okay to just sort of hang out near it and stuff, and it comes up and says hi, and then, like, if you go to pat it, it bites you. So it's, yeah, it's a bit weird. Anyway, let's move on. Okay, because there is some code that I will that I do want to write today. So I want to get into actually like a little bit of using arrays and functions, because we talked about arrays and functions this week. So there's a little bit of like, you know, there's a lot I'm asking you to think about this week. So I want to show you a little bit of both. Having said that, I'm pretty sure that we are at a point where you've learnt enough about the basic code structures to be able to use them at this point. So we know enough about looping that someone in chat has already has already come up with this idea about, given that this index is a number and given that we have loops that work on numbers, then maybe we can actually just use this to loop through an array, which is exactly what we can do. So we're going to do a really basic program that uses arrays. This is going to track the players' scores in a game, because instead of tracking marks for students, I don't really want to cause a whole lot of PTSD in the lecture. So instead, I'm going to have scores in a game. So you could consider university to just be a game, and you're trying to get the highest scores that you can in this little game. And doing the game involves, like, you know, you've got to sit through the tutorials in the game, right? And you've got to learn how the game works. You learn how to score the highest points in the game, and then you play the game. So that's what university is. It's just a game, except if you lose. Anyway, it's like, that took a dark turn. I was like, there's like this little mark on my shoulder going, "Hey, you can talk about what it takes, what happens when you lose at university." And it's like this other one's just like, "Mark, don't talk about that. They don't want to hear about that right now." It's like, okay, cool. We're gonna move on. Yes, it's a super expensive game. Having said that, I just want to say something that, like, it doesn't matter if you fail stuff at university. I failed a subject at university as well. And usually, I actually said this in an interview with, I think, the university students online. They didn't use everything from the interview, but I said that everyone should fail at least one course at UNSW on your time through, because you're going to learn more from failing a course than you're going to learn from passing them all. Just throw one. Don't necessarily throw it on purpose. It's probably going to happen to a lot of people anyway, that you fail at least one course. I don't know what the stats are. You learn that not everything should be on this one path, and there's many different ways to go about life. And having something that you might have considered a failure in the past is actually something that might teach you a whole lot. You might learn a whole lot more about how to work with your life and how to deal with the fact that nothing's ever going to go on this straight, easy path through life. Because, like, up until now, especially if any of you are like straight out of high school, you've just been put on a path and you've not been given these options to do anything. And then when you fail a subject at uni, you suddenly realize not everything is a straight line, and not everything is this kind of like direct path to, you know, high school, uni, job, I don't know, marriage, mortgage, all this kind of stuff, right? And none of that stuff is a path you have to take. And failing pushes you off that path a little bit more violently than a lot of people want, but it can open up your eyes to the fact that there is actually other ways of going about things, and you may think about things differently when suddenly you're given options. And if nothing else, you will learn a really valuable lesson about how to rearrange yourself around a changing situation. I say that knowing full well the irony. I'm talking to a whole bunch of people who got kicked out of their university for the last 2-3 months, and so you've already learnt a very valuable and not very well taught, I'm going to say, as a professional educator, the whole idea of teaching people how to live partially isolated lives away from where they were going to hang out with their friends and stuff like that via a global pandemic was not very good teaching design, and we could have done it a different way. But yeah, so you've learned that kind of lesson, and I think sometimes coming and going from things rather than like always having this perfect straight path through things can often be more valuable, because you learn how to react to different situations rather than just assuming that success will always happen, because it's not true. There's always going to be a point where success doesn't happen and you have to learn to deal with it. Okay. Life lessons. Yeah. Okay. Anyway, let's look about this. Okay, so tracking scores in a game. It's a simple game. It's got 4 players. I go 4 players because I'm a bit old school, arcade games and stuff like that. So 4-player arcade beat 'em ups are like my favorite games. We want to be able to set people's scores and also to be able to display people's scores. And if we want to be able to check who's winning and losing. And we might also, for some reason, say it's a co-op game, we want to see how many points have been scored in total. So we'll also... Past Mark, what were you trying to say? We'll also want... The game needs to know how many points have been scored. Want some way of calculating that total. As I said, not everything is perfect, so I was obviously building up to the fact that I just left half of a sentence out of my slides. So even I am not perfect, which is why, again, why Chicken, wherever she's gone, is the lecturer in charge and not me. Maybe I can blame that mistake on her. Okay, so... Mark, yes, you could come back and do COMP1511 again. What are people saying that? Please don't fail. Well, I don't say don't fail COMP1511, but there's plenty of people who fail COMP1511 who are going to end up being great programmers. It just depends on what's happening around things, and you can still be super keen on it and come back and do it and then do better. The subject I failed, I smashed the crap out of second time it did. I got an HD, and then every single subject after that had that topic in it, like every subject that followed on, I got HDs in all of them. So there was definitely for me a point where failing the course lit a fire under me. I ended up making, okay, let's just be completely honest about this. I have made from that course and the fire it lit under me to continue along that path to do better, I could say now that I've potentially made more than $100,000 from that failure, because I got work in fields related to that course and what followed on from it, and the path I took to like bounce back and decide there's no way this thing's beating me again, and then like doing better than I needed to in it and really dedicating myself to it. So it helped. I mean, if I'd been a different student, maybe I could have just gotten the HD the first time, but you know, sometimes we need those lessons, and sometimes it's good to appreciate those lessons when they happen, even when they're harsh. Okay, so what do we need to make this work? We need to create an array, and this is good because we want to be able to create an array. We want to learn how to create an array, and then if we want the players to have particular scores, we need to have ways to access individual indexes to change the players' scores. And then if we want to check who's winning, we're going to need some while loops to step through the array. And everything we're going to do, we're probably going to need to loop through the array. Having said that, let's start with the basics. Let's create the array and put some values in it. So here's some information here. For the beginning, we will just manually assign scores here. But you can see I'm doing some stuff like defining how many players I have and using that hash define to declare the array itself. Let's jump into VLab and start working on this. So I'll go up one and I'll make a directory for lecture 6. Tab complete gets me most of the way to lecture 6. ls, there's nothing in here yet. I will gedit. I can't remember what I was going to call this. Score tracker.c. You know what I might do this time? I might use a different style of variable names in this for this one, as opposed to the usual one. I use camel case a lot because that happens to be one of the things I worked in for a longer amount of time, so it just drops in by instinct. But I should use I should use snake case sometimes, just to show that it's not an absolute one way or the other. A score tracker for players in a game. Also a demo of arrays and functions. correctly. What are we in? We're still in June. Okay, so I'm going to include my standard I/O because without this, I'm not going to be able to show anything on screen, so I won't be able to know whether this is working or not. I will make my main function, and as we know, this is the output of the function, this is the input. Void is a keyword that says nothing, so there are no inputs to my function. Main likes to have a void. You can actually make functions that don't have the word void in it, and they will still just go, I don't take any input. So here I have my complete program that will at least compile because it's got a start and a finish to it. I said I was going to create the array, so one thing I'm going to do is define the number of players that are in my game to be 4, so that when I create my array, it will have space for 4 people in it. First thing I'm going to do is make my array. So I guess it's an array of scores, so I will call it scores. To make this at the moment would make an integer, but to make an array of integers, I put the square brackets. And then in the square brackets, I say, how big do I want this array? Exactly how many integers do I want in this array? And I have defined this already as 4. So it's 4, but instead of having a number like 4, I want to have num players so that I could change this. DLC expansion game is now able to handle 6 players, then I would have to come through, and all the money I make in that DLC to change this, I would be able to change this number to a 6 here. So I'm making my money, right? Okay, so there's my 4 there, and so instead of having a 4, I will use my constant for num players. So that way, when it comes to creating said DLC later, I can just change that number instead of having to go through and find all the 4s and change them. So scores equals num players. I am going to set everyone's score to 0 to begin with. This is not always entirely necessary, but for me, I'm doing this as a bit of a safety measure in case I forget to assign someone a score. At least it'll be a number that I recognize as a 0. And it sort of makes sense if the game has everyone starting at 0 score and then they build up score, then sort of I'll get away with it if I forget to give someone an initial score. Oh wow. Tiara's asked a question about a help session. Yes, there's a help session after this, and there's a whole lot of discussion in there about people trying to sort out their lives. I apologize for going on a bit of a sidetrack about what it means to fail courses and stuff, but I thought that's actually kind of useful to know as well, that it's not really... People take the word fail as like this negative connotation, but if we don't fail, we don't learn anything. So all the times you wrote code that didn't work, that's you learning more about code. If someone was going to say to you, never write code that doesn't work, then you would never experiment and you would never learn anything. So seeking failure is actually something that people talk about. Like people like, you know, do those full-on corporate productivity and TED Talks and stuff like that, but like fail faster, you know, seek out failure as much as you can because that's where you properly learn. That's actually all really good advice. I'm not ironically saying TED Talk there. Okay, I've created my array here. What was my plan here? And it has a number of players. I had a counter there. Let's not put that counter in because I'm going to do something different with this than I have in the example here. I'm probably going to do this in a function. But if we want to directly assign scores to players, I can do this like this. So I wanted to do this in the beginning, so at least show you the very basics of working with an array. So if I want to give the first player something, I can say scores 0, because I'm jumping over 0 players, so that's how I get to the first player. Scores 0 is some value, I don't know, give him a 12. I'm just giving random numbers here. It's not the same as what's in the slides, but I'm just going to put some random numbers in. Scores 1, so let's say this is partway through the game, and different players are winning and losing. Scores 3 is equal to, I don't know. I'm just picking numbers out of the top of my head here. They just all happen to be between 1 and 100, I guess. So this is my way of saying if I want to access an individual integer within the array, I use its index. And I know that if there are 4 things in here, and I skipped over 0 of them to get the first one, skipped over 1 to get the second one, skipped over 2 to get the third one, and skipped over the previous 3 to get the fourth one, I know that this is going to fill out everything that I want to do. So what I want to do now, though, is I would like to loop through this array and be able to print out the scores that everyone currently has, because something that's quite useful in say in a game that's running is to be able to see what people's scores are. So every now and then you'd want to be like, okay, current scores are this. So what I could do for that is I could make a loop, and this loop would go through the array one at a time and print out their scores. So what I can do there is, let's look at the code that we have looked at a little bit before of looping a specific number of times. And the exact number of times I want to loop is 4, because I know I have 4 elements of the array. Which means if I is less than, I'm going to use num players rather than 4, so that when I decide to change the number of players, I can easily change it. So I is less than num players. Although if I change the number of players and I've got this thing here, that's a little dangerous. So me directly assigning, if I change this to 3, would cause an error here. So it's not that easy. So that's, I am going to make some money with my DLC there, because I have to do some work. Okay, so num players here, I'm going to need my I plus plus. The plus plus is going to just increase I by 1, which means that here in this while loop, I'm just got some white space, so I'm working in the middle of the screen, it's easier for you to see. While I am looping through like this, my integer I, the first time I go through the loop, I will be 0, which will get me to this one. Second time I go through, I will be 1, because it'll have gone up by 1. Third time, I will be 2. Did I just say I will be 1? I will be 1. I'm looking at too many numbers on my screen and trying to like use my hands properly at the same time. Next time we go through, I will be 2. And the last time we go through, I will be 3. And then when I becomes 4, it will stop going through the loop. Which means that this loop will visit each element, or each index that can access this array exactly once each. So I can say, have visited I elements. So I could put this comment in here to remind myself that if I read I anytime I'm in the list, anytime in the while loop, it will tell me how many elements I've seen already. And I could also say here at the end, I is now equal to num players, because I know that it exactly reached that number. And sometimes I like to put these comments in here because what they do is they remind me exactly what I is doing. So I can do this, printf player something's score is something. I am just using integers for the moment here, but I could be using doubles if I wanted to, if I had a score that was capable of having fractions and that kind of thing. So each player is going to get a line, and we're going to say which player they are. So for the moment, we're just going to use the index. So there's going to be a player 0. Oh, actually, let's not. Let's do an I plus 1. So player 1 through to player 4, they're stored in 0 through to 3 indexes. So slightly confusing, but we'll live with that. And what their score is which element of the array we're currently looking at as we loop through, because we're looping through the indexes going through the array. So this is going to be looking at the scores array, and we're looking at the I element in the scores array. So if I run this code now, we'll have assigned these values, and then this loop will print out 4 lines, each one being the player's scores. I think this is a good point to save this, compile it, and test it. So scoretracker.c, let's make sure everything's okay over in the chat. All right, I think Dean's in there answering some questions anyway. Okay. I'll call it score tracker. And let's run score tracker. Okay, so each player's score is a certain number. If we look at these values, so now we have seen that we can store these values in the array and we can loop through an array. I'm going to take this one step further because I have a feeling that multiple times that we are running this program, we are going to want to know the score multiple times. We're not just going to want to know the score once. If I'm going to repeat actions, I guess, and I have a bunch of code that does that action, then I prefer it to be in a function than to just be a chunk of code somewhere. So what I'm going to do now is I'm going to split this code out into a function. So this function doesn't give me any information back. So since it doesn't give me any information back, I'm going to consider it to be a void function. A void function is something where I don't require any output from it. It has some consequences. The consequences is that letters and lines appear on the screen, but me as the program, as the main here, is not going to need any information back. So I'm going to call it a void function. I'm going to call it, not print players, print scores. And then I'm going to think, what information does this thing need to be able to print the scores? So it's going to need this array. So in order for this to say, I need an integer array that I'm going to print the scores from, it has to declare exactly what it needs. So I'm going to give it a different name than scores so that you know that this is a different variable. I'm doing this specifically. This is not the same variable. So you will not be getting the scores array as such. You will be getting the function itself will be kind of looking at the scores array from its own perspective. If I want to here, I can say specifically how big this array should be, or this is something that makes this useful in many different circumstances. You can give me an array and a length and I will go through that much of an array, because this array bit here is only going to tell me where the array starts. It doesn't actually have any information about how big it is, so I could give it its length as well, and then I'd know how I was going to go through it. So this is a declaration of the function. It doesn't actually have any code for the function yet, so I'm going to copy this, put it down here, give it some curly brackets that says, okay, now we're going to have some code. Give it a comment to say that if someone's going to read this, they want to know what this thing does. Prints out the players and their scores, one per line. It's always like to give a little bit of information here about what's going on. So then the code that's going to run in here is going to be a little bit different. I'm going to cut and paste this because I don't want that in there anymore. But now, instead of using specifically num players, I have a function, and the function's going to sit slightly separate. It could use num players if it wants to, because num players is a hash define that goes through the entire program. But I've been given the length specifically, so this is something that I can now use to print many different possible scores arrays. Maybe there's two teams with different scores, and the teams have different number of players. So I've used the length there to say how many things are in this array. So instead of it being num players, it's going to go up until length. And at the end of it, it's going to equal length. But it is basically the same code. So this thing is still going to take the array, and it's going to loop through a certain number of times, which I need to tell how many times it goes through. And then it will do that, and it will do the same kind of printing. So in order for me to call this function, I have to use the function's name. So I use the function's name. I'm going to assume that Dean is answering everyone's questions there. Yep. I use the function's name, which will give this main access to this code to run. And in order for this to work, I need these brackets, and I need to give it things that match these variable types here that I've created. So the first thing that it needs is an array that is of type integers, and I have an array of type integers here called scores. So in order to use that, I go scores, and then there's a comma there, and I need to tell it how long scores is. Scores, I know, is a numplayers long array, so I'm going to say this is numplayers. And so this is going to do exactly the same thing as before, but now if I want to print out scores again, I only need to use this line, and I don't want to copy paste this large chunk of code to make that happen, right? So if I want to do some other stuff and then print the scores again, then I can totally do that by using this function call without copy pasting code. So you can see how functions are going to reduce the amount of code we write and also make the main function a little bit more readable. Okay, so print scores here is going to do that. Let's save it, Control S, compile it again. I'm using my up and down arrow keys. Ooh, what have I done? Oh, right. I have a different variable in my function, but I was still accessing the old variable. Again, this is important to think about. What goes on inside the curly braces stays inside the curly braces. Scores is created inside this set of curly braces. This is a different set of curly braces, and it does not know what scores is because scores only exists between these two. Only exists here. So this can't access scores. The thing it can access is whatever array it was given as input, but it has given it its own name within its own scope of the curly brackets. So it's actually score array. Now, there is a bit of a subtlety thing going on here that these are actually accessing the same array. But that's a slightly different thing, and we're going to get into that later, what it means to be accessing the same memory from different places. We're not going to worry too much about that just yet. Okay, so we are able to access this array because we've been given access to it by it being passed into the function here. And so this means now if I compile this with the correct names in it, this should compile. Right. I'm using the up arrow key to find the last time I ran it, and it looks the same. So it is going to run the same. But what the function's done for us is it's put us in a situation now where if we want to run that function again, it's a one-liner, not a five-liner. So it makes it a little bit easier for us. Unsure if Mark sees this. What did I not see, Dean? Dennis Shah was asking, don't you need to change the... Yes, you saw it. He's behind you! Shady's asking, does the function have to go before it was called? Not all the code in the function has to be before it's called. Here, it has to know what the function is vaguely going to do, so it needs to know what the inputs and outputs are and the name of the function, and then you'll be able to call it. And then when it actually runs, it will be able to find this bit of code and run it. But in order to compile it, compiling is going to go line by line, top to bottom. It's going to have to have been declared, at least, before it's used. So, yes, it is technically possible to do this. Probably don't even need that line then. You can have that function before the main if you want to. The reason I don't do this is it's a bit fiddly and it's hard to find the main if you put a whole bunch of functions above it. I like my main to be one of the top things in the file, and also it is nice if I Control Z to undo all this stuff, put it back where it was, see my list of functions, because I could have half a dozen of these or even more. It's nice to see them in the list, and you kind of see, okay, these are the kind of capabilities we're providing here. And then later on, if you want to know the details, you can see them. When we get much later on, I'm going to show you other reasons why this makes sense, but for now, I'm going to ask you to kind of rely on me to just sort of use them as they are for now. There will be a reason why these things are separated, and we'll see it later. Alright, the tutor's answering lots of questions there, so I don't think I need to necessarily go into all of that. Okay, So we've got this, and we've done this same thing where we've looped through and we've shown the score. Now we have an array. It's going to look a bit like this, and we have been asked to find out some information. So we'd like to know who's currently winning the game. So in order to find out who's currently winning the game, we want to find out which index currently has the highest score in it. And we can do this by looping through all of the values that are stored in the array, and as we loop through, we're going to save which of these is the highest value in the array. And if we're saving which one's the highest value in the array, we're going to be able to see who's winning by the end, because we're going to compare every score we see in the array against the highest score that we've seen. So we can do it a little bit like this. This has a few assumptions in it, but we're going to do it anyway. And we're going to do this one straight out as a function, rather than like doing it and then copy pasting it across. So it's going to have an integer as output, because it's going to be reporting back to the rest of the program who has the highest score. So highest score is not necessarily what I want. I don't want to return the actual score that's the highest. I want to return who's winning. So I'm going to call it winning player. And again, since it's going to be looping through the entire array, I want it to have the score array and also know how big the score array is. So I'm going to copy this there, because it's going to take the same type of input as the print scores thing did. Okay, so now that I've decided what my inputs and outputs are of my function, I'm going to copy this, bring it down here, just give myself some space. And I'm going to say returns the index of the player with the highest score. Oops, auto-completed by accident. This also, I know this is going to happen because I know the way I'm going to do this. This is going to assume that the scores are positive in this case. So let me do this in the way that I was talking about doing things, where sometimes I write the comments before I write the code. So I'm going to say set the highest to a very low number. Then I'm going to loop through the scores array. My autocomplete keeps giving me other words to use there. So loop through the scores array. For each element, check if it's higher than the highest that we've seen so far. If it's higher, replace the highest. Keep track of the index of the highest score. So this is thinking, if I wanted to keep track of this, I actually need to have an integer to keep track of this. So let's set the highest index to a an index that's not in the array. So we want to make sure that, like, if we couldn't find a high score at all, then this thing is going to return something that doesn't make any sense. So I think these two lines can go together, because they're probably going to happen inside a section of the loop. So this might be able to help me to figure out exactly what I'm going to do. So if we say set the highest to a very low number, that means I'm going to have an integer for the highest score that I've seen so far. And maybe I'll set that to 0, because I know that my scores are between 0 and maybe 100. Oh, you know what? Let's set it to -1, because I think all my scores are positive. And so if I set it to -1, it's kind of going to let me know that if it stays -1, that something went wrong and I didn't get any information. Set the highest index to an index that's not in the array. You know what I'm going to do? int highest index. I'm going to set this one to -1 as well. So what I'm doing is I'm intentionally initializing things to values that are wrong. So that way, if my program doesn't function correctly, it's going to be really obvious to me if something went wrong, because I'm going to get these -1s back, and I'm going, oh, if I get a -1 back, it means that things didn't change properly. Okay, so loop through the scores array. If I'm going to loop through an array, then I'm going to need an iterator that starts at 0, and I'm going to need a while loop. So my while loop will go up until a certain point, and I've been told that I have the length here, so I know that I'm going to go up until I is less than length. And in order to move through the list of elements here, I'm going to want my I++. You can see I used my tab here to indent. Now gedit just turns tabs into 4 spaces. So this is indented because it's inside this set of curly brackets, so it's going to be easier to read if it's indented. Okay, so then we think, what are we going to do in here? And I actually have this stuff which actually is supposed to be inside the while loop. So I'm going to Control X to cut that and Control V here. That needs to be indented, so I'm going to tab that in. I should show you something. Oh, I can't remember if I've showed you this before. If I select multiple lines and tab, I can indent the whole line. I think I have shown you that before. So I can tab and Shift tab to move that around. And so that's tabbed there, so it's at the right indentation. So for each element, check if it's higher than the highest we've seen so far. Check if. If is a keyword that's telling me what kind of code I'm going to write here, which is handy. Set up my if statement, and I'm saying if it is higher than the highest we've seen so far. So I'm looking at the element, so I have the score array, which is the array variable that I have here, and I'm looking at each element, which means I'm using my I to look at each element, and I'm asking the question, check if it's higher than the highest we've seen so far. So the highest we've seen so far is -1. At the very beginning of the loop, that says that any value is going to be higher than the highest we've seen so far. So if the score is higher than the highest, if it's higher, replace the highest and keep track of the index of the highest score. So this looks like this wants to go in here. My indentation has gone a little weird here, but I'll make sure that that's all correct. Even the comments, I want to have them following the correct indentation, because the indentation is for humans to read. So everything that humans are going to read should be contained in brackets in the right way. Okay, tab up to that point. So if I said if it's higher, replace the highest. So highest was a variable that was keeping track of the highest number I've seen. So if this score is higher than it, this score is now the highest number that I've seen. So highest then becomes the value in the score array that I'm currently looking at. So this is me saying, if I want to find the highest number in an array, I go through the array, and every time I see a number in the array that's higher than the highest I've seen before, it replaces it as the new highest that I've seen. So it was higher than the highest, so it replaces it as the highest, but we also want to say that the highest index is equal to the one that we've seen, so that at the end of it, we can report back who had the highest score. So if I want to report back who has the highest score, it's going to be whatever the highest index is at the end. So let's step through how this would work here. So both of them are -1, and then I look at this one, and it says 12 is higher than -1. So if 12 is higher than -1, highest is now 12. And my highest index is 0. So I've got highest is 12, index is 0. And then I loop to the next element of the list here, and I go, is 76 greater than 12? Yes, 76 is greater than 12, so now the highest is 76, and the highest index is 1. And then I go to this one here, and I say, is 34 higher than 76? No, 34 is not higher than 76, so the highest remains as 76, and the highest index remains as 1, so the two values here get to stay. And again, when we look here, because 56 is not higher than 76, 76 remains the highest, and 1 remains the highest index. So we can see in this simple example how if we go through that loop, which is here, we're able to figure out which one was the highest, and we can report back that integer there. So if I'm going to report that integer back, this being a function that has a number type, an integer type, means I need to have a return, and that return has to be an integer. So I've got 2 integers here that I could possibly return. I actually have a 3rd integer here, but I very much doubt that I'm going to return I, because I is always, I'm going to put a comment here, I is going to be equal to length. So I is always going to be equal to length. That's not the one that I want to return. But do I want to return the highest score or the index of the highest player? I had said specifically that I was going to return the index of the player with the highest score. So highest index is the thing that I want to give back. Return highest index. So I've set the highest index somewhere in here by checking all the scores, and I can say this person is currently winning the game. So, stuff that I can do with that now. I can say, make a new integer, winner index is equal to winning player, and this is a function. So if I look here, the things I need to give the function, I need to give it an array and how long that array is. So I'm going to give it my scores array, and I'm going to say the scores array was num players long. So it's really similar to this one, but this one didn't give us anything back, so we weren't storing its result in a variable. And that's the difference here, but they were both taking the same input. They were both working on the same array there. So now I have an index of the winner. I can then, actually, you know what, I'm going to put a space between these because they're different. But this line is going to be a printf to say who is winning. So player something is currently winning the game. Let's put a new line on that to make it nice and neat. You don't always have to put new lines. You can actually, if you want to print out multiple things in a line, you can have multiple print statements without new lines, and they'll all just print one after the other. I do need a variable in here, and so there's the winner index. Winner index. However, the indexes were not the number of the players in the game, so I had the players numbered 1, 2, 3, 4. So I'm going to give that a +1. So now, if I run this, my path of how my program runs is different from normal. It is going line by line, but when it gets to this line, it jumps into this function, it runs all of these, hits the end of that function, comes back here. Then this one, it'll go to this function, it will run this function until it sees a return. When it sees a return, it will then basically transform this function call into that return value, which is then stored in this variable, and this variable is used to do this printout. So we're not just going line by line anymore. Some of our lines are jumping into other things. Okay, let's save this with Control S. I'm going to clear that. Don't worry about these warnings. These warnings are only based on the text autocomplete in gedit. The majority of these do not actually have any bearing on what your program is going to do. So I'm just going to clear them. I use my up arrow to compile again, and then I'm going to run this, and it's going to say player 1 scores this, player 2 scores this, player 3 is player 4's, and then it has run that loop and it has determined that player 2 is currently winning the game. Okay, so we've hit 6 PM now. I haven't finished everything that I wanted to show you in this, but I have shown you all the techniques that I wanted to show you. So I wanted to show you how we can create variables, and also I've shown you how, create variables. Mark's been teaching for 2 hours and his brain is fried. I've shown you how we can create functions. So we say what the function is here, and then we say what the code is that the function is here. I went through one of the techniques that I like to use for doing something slightly complicated where I write down what I want to do before I get bogged down in the translating of that thing to code. And then it was easier to write the code. As you can probably see, it was easier to write the code once I'd had that. The idea of how to solve this problem was one I had already, so I kind of brought that in advance to this situation. But still, hopefully that still works for you. So what we've got is a function here that loops through the list, but as it loops through the list, it keeps track of certain things in the list. So everything it's seen in the list, it's like searching for a particular thing. It's saying, I want the highest. So in order to have the highest, I need to keep track of highest out of the elements I've seen so far, and then I replace it. I left all these comments in. I didn't delete any of them. I mean, honestly, this one and this one don't really need to be there, but I'm going to leave all these comments in so you can kind of, if you want to, you can sort of deconstruct this and go, okay, this is one of the techniques that Mark uses that can come in quite handy, which is write the comments first, solve the problem in the comments, and then translate it into code. So we have created arrays as well. We've seen how to access individual elements in the arrays, and we've seen at least one really simple example of how to loop through an array, and one slightly more complex example of how to loop through an array. Before I wrap up, I should say that before I see you next, there is going to be an assignment. The assignment is going to be released. We're aiming for Sunday because it'll be a Sunday to Sunday in 3 weeks' time, so it'll be exactly 3 weeks worth of time spent on it. I've taught you nearly everything you need to know to understand the assignment, but not everything. Okay, so just if you get the assignment on Sunday and you're not sure about it, don't freak out too much, because some of the work we're going to do in week 4 pertains to the assignment. So usually it'll be the first lecture in week 4. And if you're really confused and like it's really not working for you and you don't understand anything, then hang out for a bit, because I'm going to do a separate, it's not a lecture, it'll be a live stream where, and it's like the difference is there's no slides and it's less formal, but it'll be a live stream where I will go through the assignment itself and I'll say, okay, here's the bits and pieces that are in the assignment, here's how they work. I haven't planned exactly when that will be, but maybe I will try for Wednesday at a point where there are no tutorials, or Friday at a point where there are no tutorials, but I'll find out, because I think Wednesday when there's no tutorials is going to have me doing stuff in the middle of the night, but Friday afternoon will be more likely to find a time when there's no tutorials. Okay, let me see if I had any more slides. Not really. So yeah, what we did today, theory of a computer. So we're talking about the difference between the processor and the memory and the Turing machine, which is the kind of principles under which we work. And then we looked at arrays, and we did an example that used both arrays and functions. So I'm going to wrap up the lecture here. So I'll just go into break mode for a bit, refresh my voice for a bit. But if anyone wants to stick around, ask questions as per normal, I will hang around for a little bit afterward to answer people's questions. Although I think I've had tutors answering all the questions anyway. So I'll take a break now. Also, if you do want to ask questions and get one-on-one feedback, which is like you can show your code and get someone to look at your code, the help session is running right now, and it might be, if you need help with your code, the help session will be better than me, because I can't see your code. I'm just going to give general answers. But if you want to ask stuff about the lecture, then stick around. Otherwise, the help session for your specific code, you want to know about things. All right, I'll be back in a sec. I'm back. I have a feeling, just scanning through chat there, that maybe people don't even have answers for me, because today we had a glut of tutors. We had 3 tutors in chat today, so I have a feeling that people's questions have already been answered. However, if you do have questions, please feel free to ask them now, and I'll see what pops up in the chat now and what we can talk about as answers to questions. But I think it's been really nice having the tutors in here. Always a bit like, I never want to like specifically ask the tutors to be here, because they get paid for their teaching hours for teaching you, and they don't necessarily get paid for the hours that they spend in the lecture. So I never really want to, like, you know, force anyone to have to come to my lectures just to answer questions, because I feel like that's a bit mean to them. But it's nice when they are around. Okay, William has a question. Just have a question about the lab questions. When printing patterns like X or triangle using while loop, how do you figure out the condition in the if statement? So William, this is a pretty big question, because we're talking about how we decide whether something should be drawn or shouldn't. Let me just open up Microsoft Paint, because this is an easy way to describe this kind of thing. So if I have this kind of idea, now I know that if I'm going to do, for example, a double loop, the assignment is message redacted. Yeah, you get that, Michael. I dropped a hint about the assignment in the notice. Not that it helps you, but I dropped a hint about the theme of the assignment, but you won't be able to tell. But just be patient. You will get there. You'll get there on Friday. Okay, so if I was looping through this, I would have 2 loops, right? So I have one loop here that starts at 0, 1, 2, 3. And I'd have another loop here that starts at 0, 1, 2, 3. So for each of these things that I'm going to print out, each one's going to have one number from the row loop and one number from the column loop. And whether that's rows and columns or it's I and J, it just depends on what your variable names were for it. So let's say I've been asked to do the diagonal. Where's the fill? Okay, so I've been asked, ew. Wait up. Okay. Nearly. Okay. Here we go. I've been asked to do different characters for these as for these, and I want to figure out how do I split them apart. So I can say this one, oops, let's get a brush. This one is 0, 0. This one is 1, 1. This one is 2, 2. And this one is 3, 3. This one is 0, 1. This is 0, 2. This is 0, 3. Etc. So sometimes when I'm in a question like this, I like to draw a picture and see what I'm doing. Because if I draw this picture and I draw these kind of coordinates, I'm just going to do this so you can see where my cursor is. I draw these coordinates. I can try to find a mathematical way to decide which ones I'm going to draw and which ones I'm not going to draw. And you can actually see it already. Because for the diagonal, I am going to draw the things where the I and the J, or the row and the column numbers match. If the row and column numbers match, then I will draw the diagonal. And if they don't match, then I don't draw anything. So all these other ones are not going to match, and these ones are going to match. And the entire lab this week, well, not the entire lab, but all the questions that have the double looping in the lab this week So we do some single looping questions and some double looping questions. But all the double looping drawing questions are basically about how do you craft that if statement to draw the right things. So if I'm going to draw a diagonal, this is in the tute, I think, what I would do is I'd find out, given the two numbers, what's the relationship between them that allows me to draw the diagonal. So I have, if I'm iterating on row for one loop, and inside that I'm looping on column, for example, I would say at the point where I'm inside both loops, inside the part in both loops, I would say, does row equal column? If row equals column, print this, else print something else. So that's one of the things I would do. And then more complicated things is just a more complicated question in that if statement. So you're looking at the two numbers that make up the square and deciding whether or not to print something. If you get as far as decimal spiral, then yeah, I'm not going to give you help on that. If you're pushing for decimal spiral, then you're pushing into really hard stuff. It's not really that important for the course. It's just something for you to play around with. But the fundamentals here is the double loop is going to look at every one of these potential cells in the grid, and it's going to have two numbers for each one of these, and they're all going to be unique, which means there's some kind of property that you can find. It might take a bit of trial and error, it may take drawing things out, but you should eventually be able to get the math that you need to do that. Okay. Priya is saying, I'm a bit confused about what you put at the top for the function. Let's go back to my code. We're talking about this bit, I assume, here. So, Priya, the reason why we have this here, I'm just reading what Tom's writing, he's trolling everyone about the assignment. The reason we have this here is because our main is going to use these functions. So our main uses print scores and winning player. For our main to be able to do this, and to be able to at least look at it and check if it's correct, like it doesn't have to be able to run it, it just has to check if it's correct to be able to compile it. So print scores here says I need to know that there's something in this program that matches the name print scores. And so it goes, yep, there's something that matches print scores. This, as a declaration of a function, says the function has certain elements. I shouldn't use the word elements. Certain bits. Oh man, bits is also a reserved word. See, my English is not compiling at the moment. It has certain parts that make it a function. So the first thing is the type that says this is what the function returns. This function returns void, which means it doesn't return. So it doesn't give back any information. It is called print scores, and inside its brackets it takes in some information. So it has an array and an integer. So an integer array, so integer, and it's an array because it's got square brackets, and another integer that is called length. So these names here are not super important. These names are what the function is going to use itself. So inside the function itself, for print scores, it's going to use score array and length, but those don't exist outside of print scores. So they only exist inside the print scores things here. But what this is saying is, if you would like to call the function print scores, the important things I need are an integer array and a length, which is also an integer. So when we call print scores, we give it an integer and array, because we've made an integer array here, and we give it some information, which is also an integer, about how big that array is. This is only the value of an integer. It's not necessarily a whole integer variable because it's a constant. So it's like, this is like putting this here, the number 4. So I'm going to put that back the way it was. But this information tells us what is kind of legal to use when I use the word print scores in here. And then when I go to run it, I can jump around in my code to find the code that runs it. But when we compile it, it's going to go from the top, which means it needs to have seen this line before it could see this line, because then it knows what should go into this. It's not important for all of it to be there, but that bit is important for it to know. So hopefully that helps answer your question a little bit. See you next time, Charles. I'm going to assume Charles is probably gone by now. Echoic is heading off as well. Thank you. Jeffrey, about the challenge order 3 challenges. Not sure if this is a place to ask this, but if we don't use if statements, could you give a little hint about where else we could compare numbers? Yeah. So one of the challenges is no if statements, isn't it? I'm not going to give you that much, especially because I can see there's still like more than 50 people here for question time. So I'm definitely not going to give you a solution here. But let me show you a bit of code. So int x equals 5 greater than 7. Int y equals 5 less than 7. Printf, just so that we can see this happening. X is equal to something and y is equal to something. Oh, you know what? I'm gonna use double equals because I want to write like a programmer. And this is going to have x and y as its input. It's going to save that, compile, and run that. Cool. X is equal to 0 and y is equal to 1. They're integers. Okay, that's it. Gonna delete that. That's all I'm giving you. See what you can do with it. You can potentially do something interesting with that, but who knows. Charles is like, thank you, except for you, Tom. No thanks for you, because Tom's hiding what the assignment is. Also, we had Dean in here earlier. Dean has written the majority of this assignment, so this was Dean's turn to write one. Robert is asking if using a for loop will be like, will you lose marks for it? You're not going to lose marks for it. If the stuff works, it works. I would suggest you use what we've taught you in the course, because everything then refers back to what you've been learning better. Because like the reason for the assignment is not for people to show off what they already know about coding. The reason for the assignment is to test whether you've learnt what we've been teaching. So I would suggest to just, at least for a matter of practice, even if nothing else, work on the assignment exactly the way that we've been working on everything, so that you can see whether you can take on this way of coding. I think one of the riskiest things that we get with people who already know how to code in a certain way is that one of the worst things you can ever do, this is more life advice, this has been a big life advice lecture from me, one of the worst things you can ever do is think that you already know stuff. That immediately closes your mind to new ideas. And the whole point of being in an educational institution, or frankly being a human being, is that learning new stuff is really cool. So I would potentially, if I was like, I could do all this with for loops, I would go, well, why don't I try doing this with while loops? Because if I can do it with for loops, then there's no point me doing it, right? I've already got that. I've got that proof that I can do that way. What if I try doing it another way, and maybe I'll see things differently? I mean, while loops and for loops are not that different, so this is not a big example of this, but in terms of a mindset and an attitude, it does make a difference. Because there are going to be plenty of times where you have to do things in a different way from the way that you're used to. And getting around to the habit of shifting the way you do things, reacting to different situations well. I mean, that is technically the definition of intelligence. When we talk about it in a very scientific sense, a creature is thought of as being intelligent, or measured at different levels of intelligence for its ability to adapt to changing situations. So I think it's interesting and that's what like order 3 is. It's like, can you use a limited set of tools? If you can use a limited set of tools to still solve a problem, that shows that you can react to different kind of difficulties of problem solving. So I think it's I would suggest to to try to leave behind the things that you've learnt previously and try to work within what's happening here. But I know that's not necessarily going to be the case. You're definitely going to leverage things that you've done before. But if you can, it's handy. So that's the Yoda slide that I put up in week 1. You must unlearn what you have learned. Anyway, that was a long answer to that question. Mike has an actual question. How important is knowing the theory of the computer stuff? Maybe you missed the connection, but seemed kind of unrelated to arrays. It was only vaguely related to arrays in terms of thinking about memory. I would say that the theory of the computer stuff will become very important to be able to learn other things later. So again, this depends on your context, and every course that you ever do is going to be reflected in your own context towards the situation. It's like my words are getting really vague there, right? If, for example, you're a chemical engineer who is unlikely to be doing a lot of programming in their work, but took this as an elective because you heard that there was a cool cat in it. Oh, look at her. Yeah, you heard that there was a cool cat in it and you just wanted to watch the cat, then you don't necessarily need to know how the computer works as a fundamental thing. You could also consider the theory of the computer and the arrays are two separate topics. But I did want to talk about how memory works in a computer before we started using bigger chunks of memory, because it can get confusing otherwise. So there isn't, you don't need, we're not going to be putting the theory of the computer stuff in the exam. So we're not going to ask you what different types of memory are and stuff like that. I put that in there as a purely educational thing. So that's something for people to think about, especially if people are going to be using computers at that level of detail later. So hopefully that answers the question. Liang is laughing at something, but I'm not sure what thing I did. The example makes your head hurt. Was this the chat that appeared when I started doing the number stuff? Or something? I'm not sure. Anyway. Masony, will today's code be put up on WebCMS? Yes, it will. As opposed to last week's code where it went up on WebCMS like 3 or 4 days late because I just forgot to put it there. Thank you for reminding me. I will try to make sure it goes up tonight rather than later. Also, I left out stuff because we ran out of time. So there's actually more stuff you can do, but I leave that for people to try themselves because both the other things to find out who's currently got the lowest score and what the total is of all the scores, I hope people can kind of extrapolate that from the code that I did. Definitely the lowest score is really easy because all you need to do is just reverse some stuff here and then you'll be able to do who's got the lowest score. I mean, there's some weird stuff here with this because it's harder to get the lowest score if you don't know what the maximum score is. So you'd have to figure some way around that, but I'm sure people could figure that out. So Taylor's saying if row is equal to column. In that example that I was showing here, yeah, I think that's what you're talking about, right? Yeah, if you wanted to do an if statement there, row is equal to column. I should have put timestamps on this thing so I could tell what people are actually looking at. Yeah, people are talking about rows and columns there. William is saying, if we have a 3x3 or 5x5, do I know the if statement to draw an equilateral triangle? Off the top of my head, I don't. I think in order to draw an equilateral triangle, I would need to think about where I wanted to place the sides and what things needed to be where, and then once I'd done that calculation, I would have 3 equations of lines. So if I have 3 equations of lines, I would have certain things that would match those lines. So it's kind of like I would have which pixels, getting into graphics here, which pixels would need to be drawn, and then decide which pixels need to be drawn based on that. Is that actually even one of the questions? I don't think an equilateral triangle is one of the questions, because that seems a bit hard. Because you'll have points that aren't exact points, because the equilateral triangle is not going to be on a 45-degree angle, so it's not as simple as this. So that would be very difficult. I know hollow is not too hard, because depending on where you do the other things, you'd have, okay, this line, and this line. And so if it equals any one of those, it gets drawn. Did I just give away one of the lab exercises? I probably did. Yeah, but a lot of this stuff is this, and this is the reason why we have these kinds of questions, is we need to teach you that computer science is not programming. Programming is part of computer science, but computer science is about solving difficult problems. People are relying on computer science to solve some of the world's major problems. Like, they're relying on people like us to build effective artificial intelligences to solve the world's biggest logistics problems and stuff like that. And so while that's happening, we're going to need to be people who can look at a problem and find out some kind of procedural, abstract, mathematical way of solving it. So, question of how to draw a triangle is an interesting one, because it's not immediately evident how to do it, and this will build up your capability to solve the problem, and then also you need to learn how to translate that into code so that it works. Okay. Jen says, hi, do you have any advice on approaching double loops questions in general? I understand loops, but can't seem to dissect the question and know what to do first. So Jen, my suggestion is visual. Whenever you're doing double looping, it's always a square grid. So, or it's not square, because the double loop can have different numbers for rows and columns, right? But you could consider it a grid of squares. And if you think of it as a grid of squares with this kind of information in it, it changes how you think about it significantly. Because us as humans, we're pretty good at dealing with flat surface. Our brains are actually made like that. I'm not sure, like, well, I am kind of, I know the evolutionary theory behind this is that we evolved as creatures who live on the surface of a planet, and so we treat that surface as a flat space, and so we're reasonably good at thinking in 2 dimensions. Birds are much better at thinking in 3 dimensions than us, because they've evolved with the ability to move up and down in a way that we don't. But drawing things on a bit of paper in 2 dimensions is a really good way to think about looping within loops. So this is just 2 loops. So one loop is going down these rows, and every time this loops, this thing loops multiple times to draw this. And so then we get this idea, which is why most of our first examples of trying to do a loop within a loop are really visual, because it makes it easier. So what I would say is start thinking about using a pen and paper, or for me, Microsoft Paint or something like that, to start your thinking process before you start thinking about the code. Because if you can solve the problem here, like when I drew these diagonals and then I drew the coordinates in, it became really easy to decide how to draw the diagonal, because you just look at the numbers and go, well, there's an obvious relationship here. So sometimes that's a good way to approach the problem. One of the worst things I see students, not just students actually, like full-on professionals do, is they start coding before they've solved the problem. And then you're trying to do 2 things at once. And it's very, very difficult, because it takes all of your brain to translate the solution to the problem into code, and it also takes all of your brain to figure out what the solution is from an abstract sense, from a mathematical sense. So it's better to do one of them, and you can solve the problem in the abstract way before you even start coding, and then you go in and do the code. So for example, I already had here the idea in my head of how I was going to do this. I was going to move through the array, and every time I saw a high value, the highest value, I would pick it up and then move along, and if something was higher than it, then I'd replace it. And so I knew that I had this kind of mechanism that I wanted to do of moving along the array, picking up the highest number. So I could write that all down, and then only after that translate that into code. And you saw how I wrote it all down, and then I had this comment at the end. It was like, oh, keep track of the index. And I'm like, oh, in that case, I need to go back here and add a comment here to do this. And then I go back and write the code, and it's easier because it's more likely that the code is going to be correct the first time I write it, because I've already thought through the order that I wanted to do things and that kind of thing. Okay, hopefully that helps you, Jen. Michael is saying drawing an equilateral triangle in a square grid sounds impossible. It's not entirely impossible, but it depends how much anti-aliasing you want to do. Let's not go into that. Let's okay, this is can of worms, and Mark's opening this giant can opener here. At some point, I will teach people how to do anti-aliasing, but that might not be for a few years. Yeah. I was like, I want to do it now. I was like, you know how hard it is? How hard it is for me to not teach stuff like that, because I know that I'll be here for the next 3 hours if we do that. Okay. Priya, void and int are both types of functions. Yes! I'm glad that that's clicking now. So functions have types in the same way that variables have types. And so a variable has a type for saying, this is the bit of memory that I'm going to use to store something in a particular format. So an int is a whole number. And an int for a function says, I'm going to give you back something that is exactly of that format. So a whole number format. And then, if it is an integer function, it means that if I call this function, I can treat it as if it was an integer. And so I can take this and say, you're a function, and because you are an integer function, I can assign you immediately to an integer variable, and it will work. So that's one of the nice things about it. Catherine is saying, so the score array in the print scores function actually a different variable thing from score array in the winning player function. Yeah, they are different. So if I wanted to, I could call this blah. You can tell it's getting late and I've been lecturing for a while. Where is it? I'm going to call this... Well, if I was going to do a replace of these in here and call them blah, that would all still work fine. Yeah, so these aren't the same variable. These, any variable that is in a function in the inputs is not created until these brackets open, and then it will disappear when these brackets close. So they exist only within this function, which means that they can be anything they want to be. They can be the same names as other things, because at no point are these two functions going to be able to access each other's variables. They're contained within their own curly brackets, so since they can't access each other's variables, they can have the same name, because these are never going to be accessed across each other, and the main can't see them either. I should just get rid of that blah. Yeah. So yeah, they can have the same name and not be a problem. Priya saying, thank you, you're welcome. Hopefully that does make more sense. Mason is asking about not doing a perfect equilateral triangle. So this is a super difficult thing, right? So let's do this thing here. So let's say we have an equilateral triangle. I'll do it in orange. So the equilateral triangle. Maybe? Mark, triangles don't have curves as sides. Shut up. So it's going to look a bit like this, which means you need to decide which of these get drawn. So do you draw all of them? That is a drawing of an equilateral triangle, or do you draw only some of them? That's the difficulty. And again, we can go real deep here. This is one of the most foundational things of computer graphics, in that we do have on our screen a series of square dots, and we have to decide which of the ones we're going to fill in and which ones we don't. And that's a decision. And there's many different ways of doing it. So I'm not going to be able to answer that question for the equilateral triangle perfectly, because everywhere this line crosses could be considered to something you have to draw, or you could say I have to be closer to the center than the edge to draw. It's like, how do you even do that, right? So the question of can we draw an equilateral triangle is undoubtedly yes. Undoubtedly we can draw it, but will it look correct to us? Bigger question, right? Harder to say. Roy's asking for a hint for spiral. I can't give you a hint more than spiral is going to have some idea about whether things should or shouldn't be drawn. and it is going to have coordinates for them, and there is a way to figure it out. Maybe you want to go and look up some maths for how spirals are drawn in graphs, or you want to think, it's not exactly, that's not even going to help you, but you've got to think about the positions of things and where things ought to be, and it'll depend on the size as well. So maybe it's a distance from center calculation, or maybe it's a distance from the outside edge calculation, but maybe something like that will help. That's all I'm going to say. I don't want to start actually solving the problem. Jeffrey saying, I knew that, but don't know how to use it. Should try to figure out some more. I apologize, Jeffrey, because I'm not sure which thing that I was talking about there that you're answering at that point. It must have been something that you asked about earlier. Challenge, order 3. I apologize, Jeffrey. I'm not going to give you any information than that. But I know that you can use that to do some really cool stuff. Tom, I already know how to not know stuff. Mark. Okay, Michael is saying... Oh, talking to Mason about something. Equilateral triangle, blah, blah, blah. 60-degree angles. Yeah, I assume that that's what we were talking about there with the equilateral. You could use something like this if the midpoint is less than or equal to this and that with a count. Yeah, you can do stuff like that. So Max is like coming up with ideas for how we can decide which of these sorry, I'm just pointing at my screen, you can't see that, which of these I guess characters or even pixels you would actually color in or not. Cosmo is asking if we need to put Z number inside. Cosmo, we're not going to talk about the weekly test because other people may not have done it yet. I want everyone to get a chance to do the weekly test fresh without knowing anything about it. So I definitely won't talk about it here where there's still lots of people. And Chicken is angry. Chicken is angry because we discussed the weekly test. So we won't. You can ask stuff about it, but we don't want to spoil other people's chance to do the weekly test as if they've never seen it. So we don't want to talk about it too much. That's if you were talking about the weekly test. I'm not sure if you were talking about that. Right, so people are trying to work out how to draw the equilateral triangle. So I guess there's something going on there, which is good. Yeah, you can get the gradient, because if you know they're both 60 degrees, you can get the gradient, and you can be, okay, closest point between these two to the gradient, just draw that. It's not going to end up being a straight line there, but it'll probably be pretty close. So yeah, that is a way that you could do this and it'll look reasonable, because I'm doing multiple pixels drawn for parts of the line, and that's probably not going to look as reasonable as having a single set of stars that sort of staggers whether they're vertically or angularly and that kind of thing. Priya's asking if the score tracker will be uploaded. Yes, I will remember to upload the score tracker rather than like on Sunday going, was there something I needed to do for the students? And then uploading it then, which I did last week for last week's code. Michael wants to talk about Blizzard games again. We're going to go. Okay, see you, Michael. Jeffrey's asking how do people do these challenge questions. There's a lot of mind bending going on, and I just probably need to point out that like you cannot do these challenge questions and be a perfectly viable computer scientist. They're there to potentially spark ideas in your head, but if they spark this pain of not being able to solve stuff and things, then put them away. They're not necessary. There are other places where you can learn more. As I say to people, they're not worth the time that they take. So if you have time, you can spend time on it. But if you don't have time and there are other things you want to work on, then there's probably much better learning to be done about, say, functions and arrays at the moment, rather than bashing your head against the challenge exercises for a while, because they can really cause some problems, the challenges. And Liang's saying, pretty sure everyone who does challenges has some sort of programming experience. It's usually, yeah, it's usually programming experience and or like a lot of like logical puzzle solving and stuff like that. I mean, a lot of them are not. I don't want to say this necessarily, but some of them are not that useful in terms of learning stuff. But they will just teach you something along the side of it, and they might, even if you don't solve it, they'll just get you thinking about programming in particular ways. Liang's asking if there's a club at UNSW where you can learn to build your own robots. I think there's a maker club, and I've seen them doing stuff with drones. Whether that is autonomous drones or robotics in particular, but I think they would be the best place to start. And if there is a specific robotics group, they'll probably know about it in the maker club. I think they're still pretty active. I don't know, like no one's active during COVID, but maybe they will be a little bit. And Priya's saying Mechsoc. So Mechsoc has mechatronics in it, which is like one of the big sort of physical building of robotics fields. Tom says if you print one character and squint, you get a triangle. Good stuff. Even better if it's an A, capital A. Cosmo's asking if there's a difference between return 1 and return 0 in the int main void function. The only difference between those is what the indication is of something. So it's an old convention in programming that we return 0 if everything's okay. 0, oh, okay, kind of. But you return any other number if there's an error and you want to report that a type of error has happened. So in previous code that I showed, we returned 1 when something didn't work. So when we were exiting the program because we thought that things weren't working properly, we returned 1. But if we made it to the end of the program correctly, we returned 0. So you can think of it like that if you want to, that the return 1s were put in there where something was wrong, and the return 0 was where things were okay. So 0 for okay is the way I remember it. That is only that's only if the program, if there's another program that's sort of checking for those output codes, because you notice that when we run our programs, you never see that output. So it's only if you're doing it a specific way and you're tracking that. But we tend to still follow that convention anyway, because we can kind of read it. Where we see a return that's not 0, we think that something might be, like we know that that's checking for an error case or something. Oh, Jeffrey. It's tough. Look, at no point am I ever going to say that learning new things is easy. Because if learning new things was easy, then the whole world would be a better place. Because we would all have an easier time shifting our attitudes from different things. Sorry, just crossing over into the real world a little bit too much. But, you know, yeah. If it does hit the point of, like, you know, you're thinking mental breakdown, that kind of thing, buzz us, talk to your tutor, maybe send an email to the CS1511, go to a help session, and remember that you don't need everything. Like, I'm going to be, like, straight out honest with you. When I finished the equivalent of COMP1511, which was Comp1A, back when I did it, I couldn't use pointers. Actually, it wasn't even in a language that had pointers, but even after doing the course that had pointers in it, it was like maybe 6 months later before I could use them. I haven't even shown you what pointers are yet, but that's coming sooner or later. Yeah, there were concepts that I was teaching that I now teach that I just didn't get. And it took me, like, you know, the next couple of years of cementing these concepts for them to actually sink in. So my advice is always going to be patience. A lot of these things are really easy once you've had time to learn the basics and then move on from them. And there's no point rushing the basics because everyone can benefit from it. If I was to take all the lecturers in CSE through Comp1511, only a few of them would be able to get 100% in it, and a whole bunch of them would come out of it. I know this because this is what happened to me when I started teaching fundamentals again, was a whole bunch of them would come out of it saying, man, my code was pretty bad. And I've gotten better code since going back and learning the basics again. So only some of the lecturers who are like regularly doing the low-level code will have kind of great code all the time. A lot of people are off in other directions and stuff. And so the basics are super important, and they take a while, you know. So don't worry if this is something that requires you to kind of sit back on the urge to know everything and know everything fast, because the need to do that is a pressure that doesn't relate properly to actual learning. Actual learning is something that filters in slowly and it becomes a part of you, as opposed to like cramming the hell out of something so that you can pass an exam and then moving on and forgetting it all. When we think about being able to build up these lifelong skills of problem solving and stuff like that, we just need to learn them slow, and we need to learn them over a long period of time. So there's a bunch of stuff that I teach you that you won't have learned by the end of this course, but they'll be set up for you to learn them later, and that's okay. And I think if you come into it with that kind of thinking, it'll be easier when you see things you don't know or can't complete in the course. Right. Hopefully that helps you. Any courses that use C++? Yes, there are. I wonder if Tom's already answered that one. No, he hasn't. I can't remember the name of the course, but there is a C++ course. Yeah. Sorry, I don't know how to pronounce. Is it Quindone? I don't know. Does Animal Crossing count as gaming? Of course it counts as gaming. It's just because a game doesn't have established tropes of previous games doesn't mean that doesn't count as gaming. In fact, I would say that Animal Crossing is just part of a massive genre in gaming, which is about what is it? Management, trading, open world crafting, and social aspects and stuff like that. And you'll find parts of Animal Crossing finding their way into a bunch of other games that are considered to be more harder games. Like, games don't have to be a challenge to be interesting. You can be fully entertained by something that doesn't challenge you at all. Like, hence the entirety of Hollywood. But, you know, right? So it doesn't, yeah. So I would say yes, Animal Crossing 100% counts as gaming. But I don't know why I even answered that question. Because, again, and I say this again because I had to say this last week, using me as an authority for something that is not what I'm teaching you about in the course I'm teaching you about leads to awkward kind of things, because people, I'm happy to be your authority on the fundamentals of programming and stuff like that, but I answer questions about gaming a lot because I've taught people how to make computer games, and I've pretty closely linked to the Sydney computer game industry and stuff like that, so I can answer those. But if people are going to ask me questions about things, like, I got asked once whether sushi was good or bad, and the student was so funny. They're asking all these leading questions. They're like, would you eat raw chicken, Mark? And I'm just like, no, I don't think I'd eat raw chicken. They're like, so would you eat raw fish? And I'm just like, you were baiting me with that earlier question, weren't you? So that I would answer a particular way. And the two students are using me to basically adjudicate on this dispute because I was their lecturer. And it was like, no, you can't ask me things that I'm not teaching you about, and not and then take that as if it's an authority. So you can take me as, so if I answer questions about games, the only authority I have is that I've taught them for a while, and a lot of my friends make games. But that's the only authority. But if you ask me something about how to write stuff in C, or how to start my educational journey into learning programming, then yes, I am the authority on that here at UNSW, in a sense. I'm not the only authority, but I'm one of, and so I can answer that in an official capacity. So it's always funny when people ask me questions about other random stuff. Oh, Tom, it was, should you put your ZID in your test file? Yes, I apologize, Cosmo. I had no idea what your question was, and I got that entirely wrong. So thank you, Tom, for clarifying that one. And Tom saying you should sacrifice something to Chicken, the god of computers. Yes. Alright, Catherine had to run. See you later. She's probably already gone. Oh, people looking for the clubs with, yeah, create was the one. That's the maker club. I had it wrong. Um, Jeffrey, I hope I'm helping you because you're saying I have some wise words. Oh, and you're saying to this day you still think about if you should have chosen comp sci instead of what you've already chosen. Your choices are not locked in, by the way. I had a student, one of the tutors actually, who had finished a finance or an accounting degree. Had finished it. COMP1511 was the final subject that they needed to complete that degree. They had a job lined up. So they had a full-time auditing job lined up as a graduate for this year. And after doing Comp 1511 as their final subject, they graduated from their other course and immediately re-enrolled as an undergrad in Comp Sci and is starting all over again in computer science. And got a tutoring job as well because they were that good at what they were doing. And so they found a different calling, and it's never too late to switch, you know? So I spent, I don't know, 10, 15 years programming computers, all the while kind of knowing in the back of my head but never acknowledging it that I'm better at programming humans than computers. So programming humans means the idea that I'm better at putting ideas into your brains than I am at making ideas into code. I'm good enough at it that I can teach it, but I feel like I am very much better at working with people than I am with computers, and I much prefer it as well. And so these switches and changes are things that you can do, and you can do them at different times, and it doesn't have to be that you're completely locked into one thing. I think that's what I was trying to talk about at the very beginning. In week one, I was talking about, like, you walk down UNSW and throw a rock in a random direction, you'll find a discipline that's completely different from your own, and it has a whole world of things to discover there, and there could be some amazing stuff for you there. So you never know. Oh yeah, Tom was saying, which course is the C++ course? Oh, there's courses that teach it, but are there courses that use it? I can't remember. I also don't know enough about the courses, so I think that's something that I would ask, like, maybe CSC SOC people about, because there's enough people there that they would be able to do it. Oh, Quinn's a gamer girl. That's cool. You can be a gamer girl. I don't know if you're doing the SpongeBob text on purpose there or whatever. Yeah. I mean, it's always funny because, like, people like to, like, shit on girls for playing games, and that's a really weird thing to do. So I've got a friend who's a programmer, and she's female, and she always cops that kind of shit all the time. It's really annoying. So if you want to know, like, a friend of mine, female programmer, have you heard of the new Avengers game that's coming out? She's worked on that, and she worked on a bunch of the Lego games that had happened previously. Some of them got really famous, like the Lego Star Wars games, a classic, and stuff like that. And so it's like, it's always annoying when you get kind of like, when people get pigeonholed into, like, being the other. It's like there's all the programmers, and then there's the female programmer, and she's like really gets the shits at that, and I can fully understand that, because, well, I don't really understand it because I've never been ostracized as a programmer like that, but I can understand why she would be angry and that kind of thing, because she's a better programmer than most of the guys around her anyway. I'm not sure whether that's what you were meaning by that or where you were going, but anyway. Liang's asking if mech engineering is closer to comp sci than electrical. I'm not sure, but I think electrical is kind of closer. Not sure. But again, I think Tom and I are both like, don't really know. I think you'd need to talk to someone who knew about the different schools in the way that I only know about comp sci, and I don't even know everything that's happening in CSE. It's too big a school for one person to know everything. So maybe if you talk to the student nucleus about that, they would be able to find someone for you, be able to help you with that. I'm so behind on the chat here, people talking about sushi. I love sushi, but anyway. People asking you about course advice and stuff. I think I'm not someone who should answer this anyway. Yeah, and Tom's saying we have tutors who have nearly finished law, med, and is that accounting, I think? Yeah. So we've got all these people from different fields. Some of our tutors are not even CSE students. They've just done some CSE subjects. But they were just not good at the subject as per se, but good at helping people through it. The things that I love about a lot of our tutors is they know the struggle. So a lot of the tutors will say things like, I don't even know why I was picked for tutoring. I was really bad at COMP1511. And I'm just like, that's exactly why I picked them, because they are people who can help people who think that they're bad at it, but they're not actually bad at it. Okay. Eric's saying, planning to do comp sci with mech next year, mechatronics. Yeah, you can totally do comp sci with mechatronics. I know several people who are doing that. I'm working with them on some other projects and things. Anyway, oh right, yeah, mechatronics has the computing stuff in it, but you want to do a comp sci degree as well. Cool. I don't generally give advice on degree programs because I don't really know how everything works there. I've got a very skewed perspective where I'm just like, I start a comp sci degree from where I am, and then I don't know what happens afterwards. I know a bit about it. I know where you end up because that's more recent for me, but I also don't know how the university has it set up nowadays. Jeffrey saying thanks. It's 7. Yes, and you maybe have a look at the challenges, but don't burn yourself out over it. I apologize if I am pronouncing your name wrong. Is it Quinn or so Quynh? My Vietnamese pronunciation is pretty bad, but I assume it's a Vietnamese name. I don't know. I'm going to have to wrap it up, so I'm apologizing there that I can't necessarily explain all the functions right now, but bear in mind this is not the last time we're going to see them. Next week your tutorials and labs will have some functions and some arrays in them. It also, I think the help session might still be going. I am actually pronouncing it right. Yes. I try. This is something about lecturing hundreds of people at a time, is I really want to get names right, but it's very hard. Lots of different names. So there will be more learning about them. So give it some time. I apologize because now I'm a bit tired and I'm super hungry right now, so I should go off and have dinner ready an hour over time, so I'll wrap it up now. But thank you all for coming. Liang's asking if my student number starts with a 33. No, my student number starts with a 2. Haven't you noticed that? Like, there are places in the web CMS and stuff like that that actually say what my ZID is. So my ZID is actually the ID I had as a student, because once I'm in the UNSW record and I come back to work, they're like, oh, we've actually got a record for you here and stuff, and so like they just kept the same number. Anyway, thank you very much. I'll see you all later. I will send out notices about the exam and reminders about the weekly test, not exam, assignment when it's released and stuff. You can tell my brain's finished for the day. So I will see you all soon.